technology issue. Let me welcome you all to the third day of AICTI-funded Faculty Development Program on recent advances in earthquake engineering. Today, we will be having 3 sessions. The first session will be handled by Dr. Rohan Bhaskar, Senior Project Officer, National Center for Safety of Heritage Structures, IIT Madras, from 9 a.m. to 11 a.m. on the topic Recent Advances in Seismic Fragility and Vulnerability Modeling. The second session will be dealt by Dr. Deepa Balakrishnan, Professor, CE Department, School of Engineering, Cochin University of Science and Technology, Kerala, on the topic Earthquake-Resistant Construction Techniques, from 11:15 to 1:15 p.m. And then the third session will be handled by Dr. Sachin A.S., Associate Professor, NIT Calicut, on the topic Salient Features of Recent Earthquake Codes and the Design of Special Structures, from 2 to 4 p.m. in the afternoon. Once again, a warm welcome to one and all present here. Now, let me welcome Dr. Abhilasha P.S., Coordinator of the Faculty Development Program, to introduce the speaker of the first session. Ma'am, please.
Thank you, Ampli. Namaste and very good morning, dear all. Let me share my screen. Meanwhile, hope all of you are doing well and enjoying all sessions of our FDP. So today we have with us Dr. Rohan Bhaskar, Senior Project Officer at NCSHS, Department of Civil Engineering, IIT Madras. And his session is on recent advances in seismic fragility and vulnerability modeling. Dr. Rohan Bhaskar is a structural engineer, and as said, he is currently working as a Senior Project Officer at National Center for Safety of Heritage Structures, NCSHS, in the Department of Civil Engineering, Indian Institute of Technology, Madras, India. And he did his PhD in Civil Engineering from IIT Madras and also Master degree in Structural Engineering from IIT Madras. His doctoral thesis was centered on developing a seismic fragility model accounting for the level of torsional irregularity in low-rise, non-ductile, RC moment resisting frame buildings. He worked as lecturer in the Department of Civil Engineering, AWH Engineering College, Kozhikode, from 2012 to 2013. And he was the coordinator of Structures Research Forum, IIT Madras, from 2016 to 17. And his research interests include seismic assessment of reinforced concrete and masonry structures, risk and reliability analysis, nonlinear structural analysis, and applied machine learning. He is author of multiple international journal papers and has served as a reviewer for many international journals. So we have such a dynamic person with us, and to handle our first session of today, that is third day of Untitled FDP. And so we are eagerly waiting to listen and study from you, sir. Warm welcome, sir. Platform is yours.
Thank you so much, Dr. Abhilasha. First of all, let me thank the faculty members of Vidya Academy for inviting me for this session, especially Dr. Abhilasha and Dr. Justin, who've taken so much of pain in organizing each and every session, making sure everything is happening in the right manner. So thank you once again. And if everything is okay, can I proceed with the presentation?
Yes, sir. You can share your screen now, sir.
I'll share the screen now. 1 second. Just give me a minute. My system is a little slow, so.
It's okay. Network issues and system issues, it always happens.
Yeah. So let me just put this on slideshow mode.
Yes. Just come master. You can see your screen also.
You can see the screen. I can't see my screen. Okay. I hope it's visible now. Is it visible now?
Yes, sir. Yeah, it is perfectly okay now. It's full screen also. You can see.
Okay. Okay, so good morning, everyone, faculty members and dear students. Today, I am going to discuss a topic which is typically not covered in an academic curriculum, which is on recent advances in seismic fragility and vulnerability modeling. Is my video off? One second. Yeah. So this session is going to be on recent advances in seismic fragility and vulnerability modeling. And this is a topic which is not typically taught at an undergrad or a postgrad level. So I think this will be something which is new to most of the audience here. But I think this will open doors to a lot of possibilities for research and higher learning. So without further ado, I will proceed with the presentation. So I think it's well known to everybody that earthquakes have been responsible for numerous death tolls and for wiping out economies in the past. So what I have here on the first slide are two tables. The first table indicating the 20th century's most lethal earthquakes. When I say lethal earthquakes, earthquakes which have resulted in the most number of fatalities. And in the next table, I have a table which furnishes earthquakes that have resulted in the maximum economic losses. So if you just go through the table, what you can see is that the destructiveness or the potential aftermath of an earthquake is something that cannot be taken lightly. So for example, the first earthquake that you see in the first table has caused a fatality of 2,42,800 people. That's close to 2.5 lakh people. So, and likewise, if you look at the economy side also, you can see that some of the earthquakes have been responsible for nearly wiping out 40% of a country's GDP. And this is very alarming. If a single earthquake, which lasts for, let's say, 20 seconds, if it wipes out 40% of a country's gross national product, it is something which is quite alarming. So, the understanding of the destructive potential of earthquakes has been the motive behind the development of the area, which we know today as seismic risk assessment. And the key objective of earthquake engineering on the whole is to mitigate seismic risk. So let us first try to understand what is seismic risk and what are the different components of seismic risk. Now, when I say seismic risk, I mean the different types of losses which an element or a group of elements is likely to sustain when subjected to earthquake action. Okay, so if an earthquake were to happen, how much of a loss would we expect in a single element or a group of elements? When I say element here, it could refer to a building, it could refer to a bridge, it could refer to a nuclear power plant, it could refer to a pipeline, it could be any entity. So the seismic risk associated with the region is the total expected loss which a particular region is likely to experience under the action of earthquakes over a specified period of time in the future. Now, seismic risk, like any other natural disaster can be viewed as the convolution of three important factors: seismic hazard, seismic vulnerability, and seismic exposure. Now, let me explain these three concepts in very simple terms. So, seismic hazard basically represents what is the probability of having an earthquake of a certain intensity in a particular location within a specified period of time. So what is the likelihood of occurrence of earthquakes of specified intensity? That is what hazard quantifies. Vulnerability, on the other hand, quantifies if we have an earthquake of certain intensity, what is the probability that the structures located in that region are going to get damaged? What is the probability of structural damage or structural loss if we were to experience earthquake of a certain intensity? Exposure, on the other hand, refers to the size of the population, infrastructure, etc., that is exposed to the aftermath of earthquakes. So this definition of risk equal to a function of hazard, vulnerability, and exposure is applicable to any form of natural disaster. If we are looking at flood risk, the definition remains the same, but what we perceive as flood hazard, flood vulnerability, and flood exposure will be different. But the fundamental definition remains the same. So I think let me take another example to just clarify what the difference between hazard and vulnerability is. For example, let me say I have a swimming pool with a certain depth of water. Let me say I'm putting a child into the swimming pool versus I'm putting an Olympic swimming champion into the swimming pool. The hazard is the same in either case. It's the depth of water in the swimming pool. Vulnerability, on the other hand, is the ability of the person to cope with the adverse situation. So in this case, we will know that the child is more vulnerable to drowning compared to the Olympic champion. So so you need to understand risk in very simple terms. So hazard is the possibility of having, is the likelihood of having earthquakes of a certain intensity. Vulnerability is the susceptibility of a structure to get damaged or to undergo loss in the event of an earthquake of a given intensity. Now, from this definition, it is pretty clear that hazard and exposure are terms which that are not in our control. And it is vulnerability that we will be able to control if we want to control seismic risk. Hazard is a natural phenomenon, and it is and seismic hazard is caused by lithospheric plate movements, which are triggered by mantle convection process. I believe you had a session on engineering seismology on the first day, and I'm very sure that some of these concepts would have been discussed. So seismic hazard is not in our control. Seismic exposure is also not in our control because it is related to other factors that influence human population, economic activity, etc. So the only thing which we as structural engineers or earthquake engineers are able to control is the vulnerability of the inventory. And the determination of the vulnerability of an individual building or of a building stock is what we refer to as seismic vulnerability assessment. The significance of seismic vulnerability assessment is twofold. First, it helps us identify the typologies which are highly susceptible to seismic damage. So if we are able to identify such deficient typologies, we can completely, through proper laws and guidelines, we can completely stop the construction of such vulnerable typologies in high seismic regions. And also we can update our existing building codes to overcome to improve the seismic performance of buildings which are currently exhibiting poor seismic performance. So this is the first significance of seismic vulnerability assessment, that it helps us identify typologies exhibiting poor seismic performance. In the context of the existing inventory, that is buildings that are already there, it helps us prioritize the repair and retrofit measures. So if we know that a certain system is deficient and is not resistant to earthquakes, then we can invest our money on retrofitting, on repairing and retrofitting such structures. On the other hand, if there's a structure which has very low vulnerability and which is in a low seismic region, then we need not invest so much money on the repair and retrofit of those structures. So this is the fundamental aspect of seismic vulnerability assessment. So I've taken some time trying to clear this aspect because this is very important for the understanding of subsequent discussions. So here I will introduce you to two important terms. One is the notion of a seismic fragility function, and the second will be the notion of a seismic vulnerability function. So the first term is a seismic fragility function. So seismic fragility represents the probability that a structure or component thereof violates a specified limit state under a given intensity of ground shaking. Now, it may seem like a complex definition, but the intent is very simple. If a structure were to be subjected to a ground motion of a certain intensity, for example, PGS equal to 0.2 G or PGS equal to 0.3 G, what is the probability that certain limit states will be exceeded? I'm pretty sure that all of you are familiar with the concept of a limit state. A limit state is a state of impending failure at which a structure ceases to perform a certain intended function. So essentially, seismic fragility is the probability that a structure will fail to satisfy a certain performance objective. Mathematically, it is represented by the relationship that is shown here. FLS represents the fragility corresponding to a certain limit state. There can be multiple limit states. For example, in the design of reinforced concrete and steel structures, you are already familiar with limit states of safety and limit states of serviceability. So there can be multiple limit states. So fragility corresponding to a certain limit state is the probability that that limit state will be violated given an earthquake of intensity equal to X. Okay. Now, what are these limit states? Now, I provided a qualitative definition for the limit state, but what are they quantitatively? So limit states are quantitatively defined in terms of thresholds of different engineering demand parameters, which are related to the global or local behavior of a system. For example, let me take the example of a reinforced concrete beam. In the design of a reinforced concrete beam, you have already learned that the limit state of collapse under flexure will be triggered when the when the compressive strain in the extreme fiber of concrete reaches a value equal to 0.0035. So that is a limit state, and that limit state is defined by a certain limiting value of strain. Likewise, the limit states for structural fragility analysis is defined by thresholds of some demand parameter. So this demand parameter could be something like the drift of the structure, or maximum interstory drift. It could be the maximum base shear. It could be some damage index like Park-and-Dang index. So it could be some quantity which is related to the response of the structure under earthquakes. So the fragility curve will essentially tell us the probability that the value of an engineering demand parameter exceeds a certain threshold under a given intensity of ground shaking. So the graphical representation of a fragility function is what is called as a fragility curve. And on the right, you can see 4 different fragility curves representing the transition of a structure from no damage to slight damage, slight to moderate damage, moderate to extensive damage, and extensive to complete damage. So we can see that once the first fragility curve, that is the one on the left side of the green region, is exceeded, the structure is actually transitioning from a state of no damage to slight damage. And the ordinate at any intensity level is going to tell us what is the probability that the structure is going to transition from no damage to slight damage. So this is the significance of seismic fragility, and this is the quantity which is directly which we can directly estimate from structural analysis. Now, how do we determine seismic fragility from seismic vulnerability from seismic fragility? Now, first of all, let us recollect what a seismic vulnerability function is. So a seismic vulnerability function is a function which represents seismic loss as a function of an intensity measure. Now, when I say seismic loss, it could refer to economic loss, it could refer to fatalities, it could refer to operational downtime, which means it is the time that will be taken for repair and for restoring the structure to its previous operational state. That is another possible loss measure. Or you can even the loss of cultural value is another loss measure. For example, if you consider historical or heritage structures, if it gets damaged by an earthquake, it is something which we cannot replace. So loss of cultural value is another measure of seismic loss. So what a vulnerability function will exactly provide us is an estimate of seismic loss as a function of an appropriate ground motion intensity measure. So how do we go from a fragility curve, which you see on the left, to a vulnerability curve, which you see on the right? So as I said, fragility curves represent the probability of transition of a structure from a lower damage state to a higher damage state. So if we are able to assign certain damage value, damage factors or certain loss measures to each of the damage states that are being considered, then the vulnerability at a given intensity measure is nothing but the maximum, is nothing but the mathematical expectation of the loss measure at that intensity level. What I mean by this is, for example, if we are trying to investigate the vulnerability at an intensity level of 0.4, which is shown in this figure, it will be nothing but probability of the structure being in damage state 4 into damage factor associated with damage state 4 plus probability of being in damage state 3 into loss factor associated with damage state 3 plus probability of being in damage state 2 into loss factor associated with damage state 2, and so on. This is what is mathematically represented here. So in order to determine a vulnerability function, it suffices to determine the fragility curves for the inventory. And as I said, this is what we typically obtain from structural analysis or from seismic analysis. Now, vulnerability assessment can be done in 4 different ways. There are 4 broad ways in which you can perform vulnerability assessment. They are expert opinion method, empirical method, analytical method, and as well as hybrid method. Now, I will just try to highlight what each of these are. You need not worry about what is provided, the text which is provided on the right. I will just take you through each of these. In fact, the name itself signifies what each of these functions actually represent. So in expert opinion method, the vulnerability functions are derived based on the opinion of experts. So that means they rely on the opinion of experts in the field to tell us what will be the damage distribution in a given structure when you have an earthquake of a certain intensity. So the catch here is who qualifies as experts? Who can you call as an expert? Now, you know that as far as earthquakes are concerned, low intensity earthquakes occur more frequently. High intensity earthquakes, on the other hand, occur less frequently. So it is very unlikely that even experts in the field have actually witnessed what the damage to a building stock will be in the event of a high intensity earthquake. So this, in fact, is the limitation of the expert opinion method. One, it is prone to high subjectivity and bias, and moreover, it relies heavily on the opinion of experts or the expertise. So this is the limitation of the expert opinion method, and this is suitable only for regions of the world where little or no damage data from previous earthquakes is available. The second alternative is what is called as the empirical method. In empirical method, the vulnerability functions are determined based on post-earthquake damage data, which is collected through post-earthquake surveys. So after an earthquake, you go conduct a survey. Within that type, so you survey a large cluster of buildings, and in each building you note down what is the building typology and also what is the extent of damage which the building has undergone during the earthquake. So you use this data and you do a statistical analysis to arrive at the vulnerability functions. This is what is called as empirical method. Now, since these are based on information which is collected after actual earthquakes, these represent the most realistic form of vulnerability functions. However, these functions will be highly specific to a certain seismotectonic, geotechnical, and built environment, because we have collected the information from a certain earthquake and from a certain region. So this vulnerability function that we have determined need not necessarily be applicable to another environment in the sense another seismotectonic setting under other soil conditions or for other building typologies. The third category of and also another limitation of the empirical method is that damage data from high intensity events will be usually scarce, just as I had pointed out when I discussed the expert opinion method. Since high intensity events are usually rare, it is you will not typically have damage data from high intensity events, and typically your results will be biased to low intensity damage data. The third category is what is called as the analytical method. The analytical method is what is most commonly used today, and it is based on the estimation of damage distribution from numerical simulations. So you construct a numerical model of the structure in an appropriate software. You carry out probabilistic seismic demand analysis, and from the results you determine the fragility functions first, and then the vulnerability functions. So this is what is called as the analytical method. The drawback of this method is that it is computationally expensive and warrants high level of expertise in structural modeling and analysis. And also, if you use different methods for structural modeling and structural analysis, you will typically it will typically give you different results. You will get different vulnerability functions at the end. So this is a drawback of the this is essentially a drawback of the analytical method. The final category is what is called as a hybrid method, and hybrid method essentially combines the results from expert opinion method or empirical method with analytical methods. So as I had mentioned previously, the key drawback of empirical and expert opinion methods is that typically damage data from high intensity events are typically not available. So what you can do is you can use the results from expert opinion or empirical methods to quantify the damage distribution under low intensities of earthquakes, and use analytical methods to determine what the response is going to be under high intensity earthquakes. So this is what is called as a hybrid model, and it is a mix of the above three methods. So I have tried to capture the essence of different methods, but for further reading, I've provided certain references here. All these are excellent references which will provide you an insight into different methods and the limitations of each of these methods. So in today's presentation, what I intend on doing is discussing the advances that have been made in analytical vulnerability modeling over the past 20 years. Some of the advances, it will not be possible to cover all the advances within a time frame of 1.5 hours. So I have handpicked 4 important topics which I intend on discussing in today's session. The first topic is structural modeling and nonlinear dynamic analysis procedures. Now, this is something which is not typically taught at a postgraduate level. The discussions at a postgraduate level are typically limited to linear static and linear dynamic procedures. And today we will look at something which is a little bit more exciting, which is called as nonlinear dynamic analysis procedures. This will be followed by a brief discussion on the definition of seismic input for nonlinear dynamic analysis, the choice of ground motion intensity measure. As I had mentioned previously, the fragility function, the input variable for in a fragility function is the intensity measure. So how do you choose the intensity measure? What are the factors that you have to bear in mind while choosing the intensity measure? And the final discussion will be on the vulnerability functions for building typologies in India. So these are 4 handpicked topics that I will discuss in this lecture. Of course, there are many other advances, such as advances in soil structure interaction, supplemental devices for damping, etc., which I will not be discussing in this session, but you have multiple other sessions in this faculty development program that are going to discuss the same. So moving on to the first topic, which will be on seismic analysis. Now, let us go back to what structural analysis is. So as you know, structural analysis involves the application of the principles of solid mechanics to determine the response of a structure under a set of external actions or under a set of loads. Now, when I say determination of structural response, I mean 2 types of response. One is the force response, and the second is the displacement response. So structural analysis in general helps us determine the response when the structure is subjected to a set of loads. Seismic analysis in particular involves the determination of structural response when the structure is subjected to seismic action. Now, For seismic analysis, we have 4 broad categories of methods which could be employed. We have linear static procedures, linear dynamic procedures, nonlinear static procedures, and nonlinear dynamic procedures. So I'm pretty sure that most of you would be familiar with the first two. And in fact, I think in yesterday's session, yesterday afternoon session, I believe there would have been a discussion on linear static and linear dynamic procedures because it was centered on response analysis for structural systems. So as you know, linear static and linear dynamic are most commonly used for determining the stress resultants, which you can use for seismic design purposes. So linear static procedure, as you know, is applicable only for structures where the response is governed by a single dominant mode, whereas linear dynamic procedures are applicable to structures where the response is governed by multiple modes. For example, tall buildings, structures with irregularities, etc. So I'm not going to provide a discussion on linear static and linear dynamic procedures here. Instead, I am going to be directly looking at nonlinear static and nonlinear dynamic procedures. In fact, I am not going to be discussing nonlinear static procedures extensively. I'm going to focus on nonlinear dynamic procedures. Now, here, something that I would like to highlight here is the linear procedures are used for seismic design. Nonlinear procedures are used for seismic assessment. And what is the difference? By seismic assessment, I am trying to estimate the true behavior of structure under earthquakes. Linear procedures, the intent of linear procedures for seismic design is only to provide a set of conservative design estimates, which we can, conservative forces, which we can use for our design purposes. Nonlinear procedures, on the other hand, are used in order to determine the actual behavior of structures under earthquakes, which is nonlinear in nature. In particular, in the subsequent slides, I'm going to be discussing nonlinear dynamic analysis, which is the most ideal method for assessment of three-dimensional structures with irregularities, tall buildings, etc. I'm not discussing nonlinear static procedures here because that will be most surely discussed in the session on performance-based analysis and design. So I am leaving that for later. I will be focusing on nonlinear dynamic procedures in the current session. So let me first start off by discussing how do we incorporate nonlinearity into our analysis. So if we look at the typical BTech curriculum or even the MTech curriculum in most engineering colleges, what we see is that students are taught only linear elastic analysis, but the response of structures is seldom linear. As you know, most construction materials which we use are characterized by a nonlinear constitutive relationship. If you take masonry, the response is nonlinear. If you take concrete, the response is nonlinear. If you take steel, the response is nonlinear beyond the elastic limit. So if you look at all of these systems, you can see that true response is actually nonlinear in nature. So if we are actually trying to quantify what the damage distribution will be in the event of an earthquake, we cannot use these linear analysis procedures. We have to graduate to the realm of nonlinear analysis. And this is one of the points which I would like to highlight to my faculty colleagues over here, is that this is one area where one aspect which we need to incorporate into our curriculum, because students are graduating without any sense of nonlinear analysis and nonlinear behavior. And it is most likely the BTech people who graduate with the BTech degree that usually end up working in the industry. So these students actually walk away without any introduction to nonlinear analysis. So my humble request to many of my faculty colleagues here who are part of, let's say, the curriculum development committee would be to somewhere in the curriculum introduce an introduction to nonlinear analysis, because without nonlinear analysis, we will not be able to understand true structural behavior. We get some values from linear analysis, but that's not what reality actually is. So here I will be introducing the structural modeling procedures for nonlinear analysis. So typically in frame structures, we encounter two important forms of nonlinearities. The first type of nonlinearity is what is called as material nonlinearity, and the second one is what is called as geometric nonlinearity. Now, since this is not a session on nonlinear, completely dedicated to nonlinear analysis, I will limit my discussion to material nonlinear analysis. So what material nonlinear analysis actually tries to do is to capture the effect of material nonlinearity on structural response. So what material nonlinearity is the nonlinearity in the constitutive relationship itself. Constitutive relationship is another word for stress-strain relationship. So the stress-strain relationship itself is nonlinear for most construction materials. And how do we incorporate nonlinearity into the assessment process? Now, this can be done through two different approaches. The first one is what is called as a lumped plasticity or concentrated plasticity approach. And the second one is what is called as a distributed plasticity or a spread plasticity approach. Now, in a concentrated plasticity or a lumped plasticity approach, what we assume that the nonlinearity is concentrated to certain infinitesimally small regions in a member. So, for example, if this were to represent a beam column element, we assume that the nonlinearity is going to be limited to a certain localized region of the member. Now, how is this assumption valid? Now, typically, when you do the lateral load analysis of a portal frame, which also has gravity loads, we know that the maximum negative moments in a beam typically occur at the supports, and the maximum positive moments occur at the midspan of the beam, close to the midspan of the beam. Now, with this understanding, we can also say that if nonlinearity develops in a member, it will initiate in these zones where the bending moment is maximum. Hence, what we typically do is we introduce plastic hinges or nonlinear springs into these zones that are characterized by high magnitudes of stress resultants. The stress resultant could be a bending moment, it could be shear, okay, or it could be any other stress resultant. Now, so in the case of a beam, what we typically do is we provide flexural hinges at the ends and also at the midspan, and we provide shear hinges. Where do you think the shear hinges would be provided? Where is the shear force maximum in a beam which is part of a frame that is subjected to lateral loads? The shear force will be maximum close to the supports. Hence, the shear hinges in a beam will be provided close to the supports. On the other hand, in a column, if we were to be looking at a column in a frame, we know that the bending moment will be maximum at the two ends of the column. So just like beams, we can provide plastic hinges at the two ends of the column, plastic hinges or nonlinear springs at the two ends of the column. Or instead, what we can do is, we can provide this at the ends of the column. What about the shear hinge? Now, the shear hinge to be provided in a column is a little tricky because typically under lateral loads, you have a constant shear force across the length of the column. So if that is the case, you can place the shear hinge anywhere in the member, but typically it is provided at the center of the member, center of the column. But it is equally valid to provide it anywhere in the member because the shear force is constant throughout the member. However, if you know that the spacing of the stirrups is closer at the ends and it is the spacing is larger in the middle, then it would be more wise to provide the shear hinge at the middle because that is the section which is more likely to fail under shear. So this approach where you assume that the nonlinearities are concentrated at limited regions within a member, while the rest of the member remains elastic, this approach is what is called as a lumped plasticity or a concentrated plasticity approach. The other end is what is called as a distributed plasticity or a spread plasticity approach. Now, in classical finite element analysis, this is what you do. Here you assume that the entire material is nonlinear in nature. So in a full-fledged finite element analysis, you have each individual finite elements, and each individual finite element is provided with a nonlinear stress-strain relationship. So you can use the classical finite element approaches to evaluate the nonlinear response. But here, what you need to bear in mind is that the stress-strain behavior is no longer linear elastic, and it is nonlinear in nature. And because it is no longer linear, the relationship F is equal to K times T, that is force vector is equal to stiffness matrix times the displacement vector, is no longer valid, because the stiffness matrix, it will change at each step, because the stiffness will change as the modulus of elasticity of the members change. Okay, so such an approach where you assume the nonlinearity to be distributed across the entire length of the member or to a substantial length of the member is what is called as a distributed plasticity approach. So here I'm just making a small comparison between lumped and distributed plasticity approach. In the lumped plasticity approach, the material nonlinearity is assumed to be concentrated within an infinitesimally small zone of the member. The remaining portion, on the other hand, is assumed to be linear elastic. The second part of this is, so the nonlinear behavior may be simulated through the provision of plastic hinges or nonlinear springs, each of which have been provided with specified force deformation relationships. If any of you have the experience of carrying out nonlinear analysis in any program like STAD or SAP or ETABS, you will know that to model nonlinearity, you will have to provide plastic hinges or nonlinear springs, and you have to define the force deformation relationships for these springs. If you are looking at a flexural hinge, you will be providing a moment versus rotation relationship or a moment versus curvature relationship. On the other hand, if you are looking at a shear hinge, you will be providing the shear force versus shear deformation hinge. And needless to say, both these, either of these relationships will be nonlinear in nature, or at least elastoplastic. So this is how you incorporate nonlinearity. The advantage of using a lump plasticity approach is that there is significant reduction in the computational cost, because the majority of the member is remaining elastic. So analyzing an elastic member is fairly straightforward, and the nonlinearity is limited to certain localized zones, and hence there will be a significant reduction in the computational cost because of the reduction in the total degrees of freedom. On the other hand, there are certain limitations for this approach as well. Lumped plasticity models will provide accurate representation of structural behavior only if we put the hinges or nonlinear springs at the right locations. If we do not put these hinges or nonlinear springs at their right locations, or if we do not define the force deformation relationships properly, the results from nonlinear analysis will not make sense. If some of you have carried out pushover analysis, you will know that if you do not define your plastic hinges or nonlinear springs properly, you will not get a proper pushover curve. Another aspect here is that high expertise on advanced structural modeling is necessary if we want to calibrate moment curvature relationships, define the plastic hinge lengths, etc. Another thing that you might have to define is the PM interaction, because you know that with increase in the axial force on a member, typically columns also carry essentially carry axial forces. So when the magnitude of axial force on a member increases, that will also affect the moment capacity of a member. So the axial force moment interaction will also have to be properly defined in addition to moment curvature and plastic hinge lengths. So all of these is going to consume additional time. So whatever advantage you have in running the analysis will be compensated by the time that you require in structural modeling. So this is a limitation of lumped plasticity approach. In distributed plasticity approach, on the other hand, you assume the plasticity to be spread across the length of the member. And this provides a more realistic representation of inelastic behavior, but this definitely results in higher computational demands in terms of increased analysis time and system memory. But this eliminates the need for a priori moment curvature analysis, definition of hysteresis rules, etc., since everything will be defined at a material level, at the constitutive model level. So all you are providing in distributed plasticity approach is the nonlinear stress strain curve. You are not going to be doing any moment curvature analysis. You are not going to be doing any PM interaction analysis. You're not going to be defining any separate hysteresis models. All you will do is simply define a nonlinear constitutive model. which incorporates the hysteresis rule. Hysteresis rule is the reverse cyclic stiffness and strength degradation rule that I'm referring to here. Now, these distributed plasticity elements are capable of tracking the gradual progression of inelasticity within a member cross-section, which is within a member cross-section and also across the span. Now, this is not typically possible in a lumped plasticity model because we are predefining where nonlinearity is concentrated. So we will not be able to gradually track the progression of nonlinearity within a cross-section and also along the length of a member. And also the interaction between axial loads and bending moments are well captured in the case of distributed plasticity approach. However, the drawback of this approach is that there is slight difficulty in capturing bond slip behavior, buckling in steel members, effect of shear deformations, etc. So this is a limitation of the distributed plasticity approach, because we are not, unlike the lumped plasticity approach, where we are explicitly defining all of these terms, we are not explicitly calculating this, and we are only defining the material constitutive relationships. That is uniaxial material constitutive relationships, and everything else is calculated by the program. So it is difficult to capture bond slip information, buckling in steel bars, shear deformations, etc. in a distributed plasticity approach. Here, I'm going to end this discussion on this section with a brief introduction to what is fiber modeling. So fiber modeling is something which you would have already seen in this slide. So this figure here is actually what is representative of a fiber model. So in fiber modeling, this is a type of distributed plasticity approach. I repeat, fiber modeling is a type of distributed plasticity approach. And in this approach, what you do is you divide an entire material element cross section into multiple fibers. And each of these fibers are going to be assigned a discrete material constitutive relationship, that is a nonlinear stress-strain relationship. And what the program will do is it will use this constitutive relationship, and it will numerically integrate the material responses along the length of a member to calculate the overall longitudinal response of a member. In the case of a reinforced concrete member, for example, which a figure which is shown here, you will divide an entire cross section into three parts: the unconfined cover concrete, the confined core concrete, and the steel rebars. Okay, you can define a separate material model for each of these three. In systems where you do not expect the confinement effects to be quite significant, for example, structures which are not designed for earthquake loads, the lateral confinement provided by the ties will usually be inadequate. In such cases, you can provide a common material model for the unconfined concrete as well as for the confined concrete. If not, you have to provide three separate material properties. So all that you have to do is define these three properties, define adequate number of integration sections within an element, and within each integration section, define an adequate number of fibers. So the program will automatically integrate the material responses across all fibers using standard finite element analysis procedures, and the longitudinal responses can be evaluated easily. So this was a background to nonlinear modeling. Now let us look at nonlinear analysis procedures. So nonlinear analysis procedures are so here nonlinear analysis procedures are of two types: nonlinear static analysis procedures and nonlinear dynamic analysis procedures. Here we will be looking at nonlinear dynamic analysis procedures, which are very commonly used for the seismic demand and fragility analysis of structures. Now, the basic unit of a nonlinear dynamic analysis procedure is nonlinear response history analysis. I hope all of you know what a response history analysis or a time history analysis is. It is where you subject a given structure to earthquake ground motion record, and you evaluate the response of the structure. You calculate the entire response history of the structure. This process is what is called as the nonlinear response history analysis. In the context of earthquakes, unlike other types of loading, you typically use numerical integration techniques to evaluate what the response history is going to be. So nonlinear response history analysis involves subjecting a given structure to a given to a particular ground motion and evaluating the response history. And this is the building block of all nonlinear dynamic procedures. Here we are going to be discussing three important nonlinear dynamic procedures which are used for seismic assessment, which is incremental dynamic analysis, multiple stripe analysis, and cloud analysis. If there are postgraduate students or faculty members in the group, you would have most definitely come across these words, because these are trending words as far as the field of earthquake engineering is concerned. So I will, in the subsequent slides, I'll provide you a brief background as to what these methods are. The first method is what is called as incremental dynamic analysis. So let us try to understand what incremental dynamic analysis is and how we can use incremental dynamic analysis to calculate seismic fragility. If we know seismic fragility, I have already outlined how we can construct vulnerability functions from the fragility functions. So here I will only discuss how we get the fragility function. How we construct the vulnerability function was already discussed in an earlier slide. So what you see here is what is called as an IDA curve. This is called as a multi-record IDA curve. And I will explain incremental dynamic analysis with the help of this curve. Now, in incremental dynamic analysis, what you do is you take a set of ground motions. You take a set of ground motions one at a time. So for example, let's say I'm taking ground motion record 1. So in nonlinear response history analysis, what I will do is I have my structure model. I will subject the structure to a given ground motion record. I will evaluate its response history. That is the standard procedure of nonlinear response history analysis. Now here, what you will do is you will take the first record, and what you will do is you will carry out nonlinear response history analysis, and you will find out what the response history is. Now, from the response history, you will monitor any demand parameter that you are interested in. If you look at the IDA diagram here, the demand parameter that is monitored is the maximum interstory drift ratio. So you have a structure which you have modeled, you are subjecting it to ground motion record 1, and you are evaluating the interstory drift ratio history. And from the history, you pick out the maximum value, which is your maximum interstory drift ratio. So for a given ground motion of specified intensity, let's say of specified spectral acceleration, for example, you now know what the maximum interstory drift is. For example, for the ground motion that is located somewhere here, you know that at a spectral acceleration of 0.2 g, we are observing a maximum interstory drift equal to 0.01. Okay, so what you will do is you will take this ground motion, not stop here. You will next scale this ground motion. So first you had that unscaled ground motion. You performed nonlinear response history analysis with that ground motion. You obtain the interstory drift ratio. So you get the first point on the IDA curve. To get the next point on the IDA curve, what you do is you scale this record. What I mean by scaling this record is you multiply all the ordinates by a constant factor. Let's say you're multiplying it by a factor of 2. You multiply it by a factor of 2, then you do nonlinear analysis. Because you are doing nonlinear analysis, the value of maximum interstory drift in this case will not be twice the original value, because this is nonlinear analysis. Okay, so you take the scale record, you do nonlinear analysis, again determine the maximum interstory drift to get the second point on the IDA curve. You keep repeating, you keep increasing the scale factors and keep on doing the nonlinear analysis, and you get multiple points on the IDA curve. You just join them by a line, and that is what you call as a single record IDA curve. So a single record IDA curve will consist of the output values from multiple nonlinear time history analysis obtained using ground motion scale to different intensities. Okay, you can repeat the process using different ground motions. Typically, if you're using something like spectral acceleration, it is recommended that you use close to 30 ground motion records for your analysis. If you are working with a more efficient intensity measure, I will I will tell you what an efficient intensity measure is in the subsequent slides. You can go for a much lower number of ground motions. But if you're using something like spectral acceleration, it's best to use at least 30 ground motions. So if you have 30 ground motions, you will have 30 IDA curves, and those 30 IDA curves are what are shown here. Now, how do you determine the seismic fragility from this IDA plot? So that is what we are going to examine here. So to examine, so again, what is seismic fragility? It is the probability that certain limit states will be, that a certain limit state will be exceeded under a given intensity of ground motion. So the intensity of ground motion here is on the y-axis. So for a given y-axis value, let's say if that value is 0.4, at a spectral acceleration of 0.4 g, what is the probability that my maximum interstory drift is going to exceed a certain threshold? Let us take that threshold as 0.02 g, which is shown here. Okay, so at 0.4 g, what is the probability that my interstory drift will exceed 0.02 g? So that is the fragility estimate there. How do you evaluate this? So you have, so if you look at the intensity level of 0.4 g, if you draw a line, this will intersect each of the IDA curves at different points. So each of these points represent the maximum interstory drift ratio demand on the structure when it is subjected to a certain ground motion among the 30 ground motions considered. Okay, so you look at the probability distribution of maximum interstory drifts. How is this probability distribution varying at this intensity? That is what is shown by this pink line. Okay, and you look at the probability content after 0.02, because we are looking at the probability that a limit state will be exceeded or violated. So if you take the area of this probability density function to the right, you will get the estimate of seismic fragility at an intensity level of 0.4 g. Okay, likewise, you can do this at 0.2 g, 0.6 g, 0.8 g, 1 g, and so on. And what you ultimately get are discrete estimates of seismic fragility at different intensity levels. If at different intensity levels. So if you can use any standard procedure to fit a continuous function to these discrete fragility estimates to obtain your fragility function, which is a continuous function. So this is how you obtain the fragility estimate using incremental dynamic analysis. Now let me just go through the points which I have on the slide just to see if I have described everything in my discussion. So IDA involves subjecting the structure to a suite of ground motion records, each scaled to multiple intensities, so that a complete picture of dynamic response from elastic behavior to the onset of global instability is obtained. So when you take a given ground motion and you keep on scaling, you are actually, initially the structure would be elastic, would exhibit elastic behavior. But if you keep on increasing the scale factor on the ground motion records, you will see that the behavior becomes nonlinear and inelastic. And finally, at some point, you will see that your structure is collapsing. This is what is indicated by the flattening of the IDA curve. That is, the maximum interstory drift at that intensity level is shooting to infinity. Okay, this is what is meant by global instability. So in an IDA analysis essentially monitors the variation of various EDPs under increasing intensities of ground shaking. And a typical IDA curve is a plot of ground motion intensity versus the EDP of interest. Now, it can be any EDP. It is not necessary that it has to be maximum interstory drift. You can use other EDPs also, such as peak floor acceleration, maximum base shear, Park and Ang index, etc. The only thing that you have to be careful about is whatever EDP you are monitoring, that is the EDP that you are going to be using to define your limit states. So if I have an IDA plot with spectral acceleration and maximum interstory drift ratio, your limit states should be defined in terms of some limiting values of the maximum interstory drift ratio. Then only you can use this procedure. So this is the mathematical definition of seismic fragility, which I had already indicated previously. Fragility is the probability that my demand, my EDP value observed at an intensity level will be more than the capacity threshold, which is specified for a given limit state. Okay. And from the discrete estimates of fragility at different intensity levels, you can use standard procedures such as least square error fitting to obtain a continuous function which will fit the discrete estimates of fragility. So this is incremental dynamic analysis. The next method is what is called as multiple stripe analysis. Now, multiple stripe analysis looks very similar to incremental and dynamic analysis, and it in fact is a variant of incremental dynamic analysis. Now, in multiple stripe analysis, we will be carrying out the analysis only at very specific intensities of ground shaking. If you look at the IDA curve, for different ground motions, we can use different scale factors. All that we need is to obtain that IDA curve. At the end, regardless of what scale factors we use for individual ground motions, we end up with a procedure to estimate seismic fragility. Here, in multiple stripe analysis, on the other hand, we perform the nonlinear response history analysis at very discrete levels of ground motion intensity, so that we get these stripes of data. We get these stripes of data or ordered pairs of maximum interstory drift ratio and the intensity measure. We get ordered pairs from which we can estimate seismic fragility directly. The method which I had, since this is a particular specific type of IDA, the method that I had mentioned for IDA to determine seismic fragility is equally applicable here. The advantage here is, since you are doing the analysis at specific values of the IM, you are getting these stripes directly. In incremental dynamic analysis, on the other hand, you are carrying out the analysis at some random scale factors, and finally, you are drawing imaginary lines at different intensity levels, finding out the intersection points and looking at the probability distribution of the maximum interstory drifts corresponding to those intersection points. All this is not necessary if you do multiple stripe analysis, where if you are very careful in doing the analysis only at discrete level or discrete levels of the IM. So this is multiple stripe analysis. So multiple stripe analysis can be done in two ways. Either you can take a parent set of ground motions and you can scale them to different intensity levels as you would do in incremental dynamic analysis. Or what you can do is you can use different sets of ground motions for different intensity levels. If you do that, it eliminates the need for scaling the ground motions. You can use different ground motions for different intensity levels. The fragility assessment procedure will remain the same. Okay, so this is multiple stripe analysis. It is essentially a variant of IDA where the scaling of the ensemble is carried out in a methodical fashion so as to generate ordered pairs of EDP, IM data at discrete levels of the IM. Also, the strong motion records are scaled to target levels of intensity so that, are scaled to target levels of intensity where the scaling factor is the ratio of target intensity level to intensity level for the unscaled record, as we had done for IDA. Alternatively, you could use a unique set of natural ground motion records to be used at each stripe level, thus eliminating the need for scaling on the whole. Okay, so this is how you estimate fragility using multiple stripe analysis. It is similar to incremental dynamic analysis. Now, here I wish to highlight something which I had not mentioned when I discussed incremental dynamic analysis, but which is equally applicable to IDA. Now, what you can observe here is when you use large scale factors or when you look at ground motions with high level of intensity, we know that when we do the analysis, some of these analysis are going to result in numerical instability in the analysis. That means the structure is going to fail and the maximum interstory drift value will not be defined at this intensity, will be infinity. It will be undefined at that level. So these are what are called as collapse cases. So you can see that as per this MSA plot, at an SA average value of 0.125 G, we are observing that 3 of the ground motion records are triggering collapse, which means that if we had used 20 ground motions in the first place, there would only be 17 data points remaining here. 17 data points which we have remaining. Likewise, here 5 collapses have occurred, and hence we would only have 15 points here. Now, what do we do when we have these collapse cases as well? So at lower intensity levels, we don't have these collapse cases. So hence, we could directly draw that probability density function and just take the area of the probability density function to the right of the capacity threshold to get the fragility estimate. However, this is not possible here. What do we do here? In this case, what we will do is we will split the expression for fragility into 2 parts. That is, it is the probability that the limit state, it is the probability that the limit state is exceeded given no collapse into probability of no collapse plus probability of violation of the limit state given collapse into probability of collapse. Now, if there is collapse, we know that there will definitely the probability of limit state violation will essentially be 1. That is why the term probability of theta max greater than theta max CLS given C is missing here. Okay, that probability will always be 1. So in such cases, what we can do is we can directly establish this relationship for seismic fragility using total probability theorem, and we can simplify it further to determine the seismic fragility estimate. So I do not want you to go I do not I know that it is very complicated math here, and I do not expect you to understand this completely at this stage, but I need you to understand that there are methods to incorporate the non-collapse cases within the realm of seismic fragility assessment using IDA or multiple stripe analysis. Okay, and this has to be incorporated, otherwise you will end up with wrong estimates for seismic fragility. The third nonlinear dynamic procedure, which I would like to discuss, is what is called as cloud analysis. Cloud analysis is fairly simple. What you simply have to do is you take a set of ground motions with different intensity values, with, for example, with different SA of T1 values. And what you do is you perform nonlinear response history analysis with each of these ground motions. As you do a response history analysis with each of these ground motions, you will obtain a certain value for maximum interstory drift. So what you can see here is what is called as a cloud analysis plot. So a cloud analysis plot is nothing but a scatter plot in which you have ordered pairs of the intensity measure and the engineering demand parameter. And in this particular case, they happen to be SA of T1 and maximum interstory drift respectively. So you have this, you construct this scatter plot. And if you have the scatter plot, you can most easily construct a regression line which fits the scatter plot. So this is called as a demand model. So cloud analysis involves fitting a linear or nonlinear regression model to pairs of EDP and IM for a suite of as recorded or scaled ground motion records. So you can directly use unscaled ground motions. You need not scale the ground motions at all, as long as there is a good spread of intensities. And you assume a certain form for the regression model, and you perform regression analysis to establish a relationship between maximum interstory drift and spectral acceleration. So what this model will essentially tell you is, if I know what the value of the intensity measure is, what is the value of the maximum interstory drift? Using this regression analysis, you will get such a model, which can predict maximum interstory drift with the knowledge of the intensity measure. So what I have here is a typical form that is used. This is called as a log linear demand model, and this is quite commonly used within the realm of seismic fragility assessment. So the method is, so what you can do is, all you have to do here is calibrate this demand model. Now, once this demand, I'll just skip the next 2 points for now. I'll explain it at the end. Now, once the demand model is calibrated, we can use standard Monte Carlo simulation procedures to determine what the seismic fragility is. What I mean by that is, just look at this expression. In this, we know that fragility is the probability that the EDP capacity is less, EDP capacity minus EDP demand is less than 0. Okay, this is the expression. Now, EDP capacity is known to us. It is what we define as the limit state. Now, EDP corresponding to a given IM is given by a demand model. So what you have to do is you have this mathematical demand model. You carry out multiple Monte Carlo simulations on the demand model. And for each simulation, you check whether the estimated value of EDP by the model is less than or greater than the limit state threshold. Okay, and you just count the number of cases or the number of simulations where the EDP value turned out to be more than the limit state threshold which we have provided. And from this, you directly get the estimate of fragility. Again, what you get are discrete estimates of fragility corresponding to specific levels of the IM. Just fit a continuous function to that, and what you finally have is the fragility curve. So these are the three important items that three important nonlinear dynamic procedures which I wanted to discuss, and this was the core of today's discussion. Remaining topics are fairly simple and which we could breeze through quite easily. One important advancement that has occurred, or improvement in the understanding that has occurred over the years, is related to the definition of the seismic input. Now, we know that the seismic input for nonlinear dynamic analysis procedures are strong motion records or accelerograms. So if we are looking at a site-specific problem, we may also require accelerograms that are representative of the hazard at the particular site of interest. For example, if we are assessing a nuclear power plant, we need to know what type of ground motions are likely in the site of the nuclear power plant. We don't want to do the investigation with some random ground motions. Okay, so we may have to filter out whatever ground motions are available and choose a set of ground motions which are appropriate for the site of interest. Now, the accelerograms or the strong motion records which are used, the accelerograms or the seismic signals that are commonly used for analysis fall into one of three categories. We have natural strong motion records, artificial spectrum compatible accelerograms, and synthetic waveforms. Now, natural records are, as the name suggests, are those which have been recorded during actual seismic events at various recording stations, and these represent the most realistic type of ground motion input. Why is it most realistic? Since they are recorded during an actual earthquake, these records retain the amplitude, frequency, and duration characteristics of an actual earthquake. Okay, and the emergence of multiple user-friendly strong motion databases have allowed for easy access to natural records, and most often these are the type of records that most structural engineers work with when they are performing seismic analysis. And if you are going to be doing some seismic assessment for your master's project, or if you're guiding any student who is doing seismic assessment, this would be the best type of record to go with, because these were recorded during actual events. Other options that you have are artificial records and synthetic records. These two categories of records are typically used typically used because when we do not have natural records for high seismic events. As I said, high intensity events are associated with higher return periods. So which means that they occur less frequently. So we may not have a significant number of natural records corresponding to high intensity earthquakes. In such cases, to generate such high intensity signals, we may have to resort to artificial or synthetic methods. Okay, artificial records are those which are generated using random vibration theory by ensuring the compatibility of a target spectrum, by ensuring compatibility between the response spectra of individual ground motions and a target spectrum. The target spectrum is something that is representative of the hazard level of the site of interest. The target spectrum could be the design spectrum. You know, the IS 1893 design spectrum, part 1, the elastic design spectrum is an example. It could be a uniform hazard spectrum or a conditional mean spectrum that you obtain from probabilistic seismic hazard analysis. All these are valid options to be used as a target spectrum. Now, the only issue with artificial records is that with this procedure, since you are using random vibration theory, you will get some signals at the end, but these signals may may be characterized with unrealistic frequency content, which is not typical of actual ground motions. That is why artificial records are avoided whenever possible, because these are just a byproduct of signal processing theory. The next category is what is called as synthetic records, and synthetic records are those which are generated from rigorous modeling of the seismological source, the local site conditions, and as well as the path conditions. So this is the most advanced way in which you can derive records for seismic analysis, but this is not typically used in the context of seismic demand assessment, since it requires the expertise of a seismologist. And typically structural engineers are not that strong in seismology to all structural engineers are not that big of experts in seismology to generate synthetic records. So here I will explain something which may be very useful to some of the MTech students, as well as some of the guides who are working, guides for students who are working on earthquake engineering problems. This is just an illustration of how you can select a natural ground motion record for your seismic analysis purposes. I'm just using presenting the peer NGFS2 database interface here, just to highlight how you can select ground motions for your analysis purpose. The first means is to define a target spectrum. The first thing which you will have to do is define a target spectrum. Are you looking at a site-specific problem, or are you not looking at a site-specific problem? If you are not looking at a site-specific problem, there is no need to define a target spectrum. Otherwise, define the target spectrum. The target spectrum may be a design spectrum, uniform hazard spectrum, or a conditional mean spectrum. Next thing is, the second stage would be to specify some constraints on event magnitudes, rupture distances, average shear wave velocity, duration of earthquakes, etc. So apply some constraints on the seismological parameters to get ground motions that are represented, which are likely to occur at the site. So if you have a particular site, you know what typical range of magnitudes are expected at that site. So you filter out ground motions that are available in the database based on parameters such as the fault type, moment magnitude, joiner-bore distance, rupture distance, average shear wave velocity, 5 to 95% significant duration, etc. So these are the pre-selection constraints. Specify the pre-selection constraints, and then also specify the method which you want to use for scaling of records, and also to ensure spectral compatibility. What I mean by this is, finally, you want records that match a certain target spectrum. Okay, so there are certain settings which you will have to adjust here in order to determine which you will have to specify in order to determine how you are going to scale and ensure spectral compatibility. Okay, and finally, once this is done, once all of this is specified, you can directly extract your results. The peer database will provide you with a set of ground motions that satisfy the pre-selection constraints which you have specified and which are compatible with a certain target spectrum. What I have shown here in this diagram is a set of ground motions which I have downloaded from the peer database for one of my studies. Here I can see that the average, the mean spectrum for the suite of ground motions that I have extracted from the database is in good agreement with the target spectrum, which is indicated by the red line. Okay, so if you use this procedure, you will be able to get spectrum compatible ground motion records. Now, one more item relating to the characterization of the ground motion, which I would like to highlight in the context of nonlinear dynamic analysis procedures, is the concept of intensity measures. As I said, the fragility function is conditioned on some intensity measure, now, which is indicative of the severity of ground motion shaking at the site. And this intensity measure, in fact, is the connecting link between seismic hazard analysis and seismic structural analysis. Okay. So selection of this intensity measure is very critical to ensuring accurate results for seismic risk assessment. Now, the intensity measures used for seismic risk assessment can be broadly classified into two categories: non-structure specific intensity measures and structure specific intensity measures. Non-structure specific intensity measures are those which are based purely on ground motion characteristics, whereas structure specific intensity measures are those which take into account both ground motion characteristics and dynamic properties of the structure. So an examples for non-structure specific intensity measures are peak ground acceleration, peak ground velocity, peak ground displacement, specific energy density, cumulative absolute velocity, etc. Now, why are they non-structural specific? For example, what is peak ground acceleration? It is the maximum ordinate that is observed in the ground acceleration history right? It is the absolute maximum ordinate that is observed in a ground acceleration history. So it depends only on the characteristics of that ground acceleration history. It has nothing to do with the structure which we are analyzing. So such a measure is what is called as a non-structure specific intensity measure. Now, while these are simple to define, these many studies, particularly in the 1990s and the early 2000s, have shown that such measures exhibit low correlation with different engineering demand parameters. This is essentially because these intensity measures have nothing to do with structural properties. They do not convey any information regarding the structural properties. On the other hand, when you look at structure-specific intensity measures, they also account for some structural characteristics, some dynamic properties of the structure. For example, first mode spectral acceleration, first mode spectral displacement, velocity spectrum intensity, Hausner intensity, average spectral acceleration, etc. Now, because these intensity measures also furnish some information about the dynamic properties of the structure, we can observe that these intensity measures generally exhibit a higher correlation with engineering demand parameters compared to non-structure specific intensity measures. As a result, in the realm of seismic fragility assessment, there has been a gradual transition from the use of non-structure specific intensity measures to structure specific intensity measures, because structure specific intensity measures exhibit a higher correlation with the response. Now, in this context, I will define a term called efficiency, which is the ability of an IM to predict an EDP with low inter-record dispersion. In other words, efficiency is a measure of the degree of correlation between a given intensity measure and an EDP of interest. In this, I don't know if the font size is big enough for you to see all of this, but what I have here are cloud analysis plots in which theta max is plotted against different intensity measures. As you can see on the left side, I have left side columns, I have non-structure specific intensity measures. On the right side, I have structure specific intensity measures. As you can see, the ones on the left-hand side have much lower efficiency when compared to those on the right-hand side. For example, P ground displacement has an R-square value of 0.37, whereas something like IM Bianchini, which is a structure-specific measure, has an R-square value of 0.81. This is more than twice. It's about 2.5 times, which means that there is a significant improvement in the prediction capacity when we are using structure-specific intensity measures. And there has been not only structure-specific intensity measures, recently there has been a migration towards advanced structure-specific intensity measures as well. And why is this so? Let me explain this with the example of SA of T1. Now, I hope all of you know what SA of T1 is. SA of T1, or spectral acceleration, is the absolute maximum acceleration which will be experienced by a single degree of freedom oscillator with period T1 and damping ratio xi when subjected to a given ground motion. For different ground motions, you will have different SA of T1 values. So in this figure, what I have are the response spectra, acceleration response spectra for 3 different ground motion records. Okay. Now let's say I am analyzing a structure with a fundamental period of 0.5. Okay, and I've drawn a line here. Now, if I were to be using SA of T1 as my measure of ground motion severity, I will be able to say that the pink response spectrum, or the pink record results in the least will result in the least amount of acceleration followed by the blue line, and the red response spectrum corresponds to the record, which will result in the highest acceleration in the single degree of freedom oscillator. Now, this statement would have been correct if we were looking at linear analysis. But here we are looking at nonlinear analysis. When we do nonlinear analysis, we know that we are actually capturing the damage that is occurring to the structure. Now, when a structure undergoes damage, there is an elongation in the natural period of the structure, as a result of which there is a decrease in the stiffness of the structure, as a result of which there is an elongation in the natural period of the structure. So what will happen is when you subject a structure to earthquakes, in reality, there is an increase in the natural period of the structure. Okay. Yeah, the natural period, the effective natural period of the structure is not going to be what you determined using elastic theory. Okay. The structure is going to undergo a period elongation with increase in ground motion intensity. So whether the response is going to get amplified or de-amplified, or whether it's going to stay the same, depends on the spectral shape beyond the fundamental period of vibration. Okay, it is important to incorporate the spectral shape at higher periods into the assessment framework. So you can see that the red line, although had a high SA of T1 value with period elongation, the amplification in demands is gradually diminishing. Whereas for the blue one, although the acceleration response at period T1 was low, with period elongation, we can see that the amplification is going to increase. So this is why SA of T1 as such is not a good predictor of inelastic seismic demands, because it cannot account for the period elongation. Also, since it looks only at the spectral ordinate at period T1, it does not account for the contribution of higher modes, which could also be significant. So different advanced structure-specific intensity measures have evolved, which use some proxy for the spectral shape over a broader range of structural periods. Two important categories of such intensity measures are those which are based on integration of spectral ordinates, and the second category is those based on geometric averaging of spectral ordinates. Here, I will first introduce advanced intensity measures based on integration of spectral ordinates. So what they do, what these intensity measures do is, it does not look specifically at the spectral ordinate at period T1, but rather it looks at the spectral ordinates over a range of periods, and it uses the integral. Integral graphically, it is the area under the response spectrum to define an intensity measure. So there are intensity measures which are based on the integration of these spectral ordinates over a range of periods. These range of periods can be fixed, or it could be related to the natural period of the structure. Having it related to the natural period of the structure is more meaningful, because it helps us define a more meaningful range of periods which are relevant to the structure under consideration. So these are two examples for such advanced IMs. We have velocity spectrum intensity, modified Hausner intensity. So both of these use the area under the velocity response spectrum over a range of periods to define the intensity of an earthquake. The first one looks, if you observe at the second one, the range of periods lasts from 0.5 T1 to 1.5 T1. The periods below T1 are intended to account for higher mode effects, whereas the periods, spectral ordinates corresponding to periods higher than T1 is meant to account for the effect of period elongation. Similarly, another alternative to using integration of spectral ordinates is to use geometric averaging of spectral ordinates. So instead of integration, you can simply use geometric averaging of spectral ordinates. So you have a wide class of intensity measures that have evolved, which are characterized by high efficiency, superior efficiency compared to SA of T1. All of these advanced IMs which are based on geometric averaging are generally known under the name average spectral acceleration, denoted by average SA or SA average. Okay, you might have seen me using SA average in some of the cloud analysis plots shown earlier. Okay, so an exercise which I will leave to all of you is, once this talk is over, just go back to this slide and just draw a comparison between the efficiency of non-structure specific intensity measures versus these advanced structure specific intensity measures, which are shown on the right. Okay. The definition to all of these intensity measures have been provided in the next slides. So just do this exercise for your own understanding. One final category of intensity measures which I would like to highlight here are what are called as vector intensity measures. So as the name suggests, vector intensity measures are nothing but vectors of non-structure specific or structure specific intensity measures. So vector intensity measures consist of multiple entries.
Sir, you can have a
That's okay, that's okay. So vector intensity measures consist of multiple entries which are related to one or more ground motion components. I have furnished two different examples for vector and intensity measures. The first one has two terms. Okay, the first term is the spectral intensity at period t1. The second one is the spectral intensity at a period at a period 2t1 divided by this relative to the spectral intensity at period t1. So instead of integrating the ordinates or taking a geometrical average, you can retain it as a separate intensity term and use both. You can augment both of these two terms to get what is called as a vector intensity measure. Now, vector intensity measures may also be necessary when we are considering more than one component of ground motion at a time. Right. So for example, if we have the X component of ground motion and the Y component of ground motion, we can define PGA for the X component. We can define PGA for the Y component. So how do we define the general severity of ground shaking? We can define that using a vector of PGA X and PGA Y. So this is a context where vector intensity measures would be required when you have to consider the effect of more than one ground motion component. And all of these vector intensity measures have been shown to possess higher efficiency compared to scalar intensity measures. You can go through this reference if you want more details. But one key drawback of using vector intensity measures is that when compared to a scalar intensity measure or a single valued intensity measure, there will now be more predictor variables in the demand assessment framework. Okay, now there are more predictors. So if you have more predictor variables, you will have to carry out more number of simulations to ensure a certain amount of accuracy. If there are more input variables, you need to run more number of simulations. Okay, so that is the reason why vector intensity measures are not are used for seismic demand assessment, but are yet to be applied for seismic fragility or vulnerability assessment applications. Now, I provided a suggested reading here, which is one of my own papers published in 2020. If you're interested, if you go through this paper, I have introduced a completely new concept, which is called as bidirectional scalar bidirectional shaking intensity measure, which is nothing but a scalar intensity measure, which you can derive by combining the components of vector IMs using different combination rules. So you combine the different elements in a vector intensity measure using different combination rules, and you finally get a scalar intensity measure. And this scalar intensity measure will retain the high efficiency of the vector intensity measure while simultaneously not increasing the number of simulations. So the number of predictor variables will still be 1 instead of 2 or 3 or 4. But at the same time, you're not compromising on the efficiency. You're not compromising on the accuracy of the model. So if you're interested in knowing how I've done that, you can just go through this document. Now, moving on to the final two slides with which I will close my discussion for today, which is on the seismic vulnerability of Indian building typologies. Now, given that I've discussed all these advanced topics right now, where does India stand in terms of seismic vulnerability and fragility assessment? So if you go through literature, you will realize that it is only in 2013 that India released an official document, that is the NDMA, or the National Disaster Management Authority, released documents related to vulnerability assessment for Indian building typologies. So it's not one single document, but a set of documents that defines what are the different building typologies in India and what are the vulnerability functions to use for the assessment of these building typologies at a regional or a territorial scale. Okay. So actually, this was a project which NDMA carried out in conjunction with some of the old IITs. IIT Madras was also a member in this project. So different IITs were assigned the duty of identifying building typologies located in different parts of the country. For example, IIT Madras was assigned the South Zone. So the task was to identify building typologies, different building typologies, and then to prescribe vulnerability functions for these building typologies. So the first part of this work, that is the identification of building typologies, is something that has been very well executed. So from the study, we realize, so the NDMA document recognizes 54 different building typologies within the Indian subcontinent, 54 different typologies. So what I have shown in this table is just the different categories of concrete structures which are recognized by this NDMA document. It was not possible for me to include all 54 documents, 54 typologies in this slide. That's why I've made a reference to one of my World Conference papers. This is from the 16th World Conference of Earthquake Engineering. So if you go through that paper, you will see that the complete classification, all the 54 typologies which I listed. In fact, this table was later used by the global earthquake model to develop the seismic exposure model for India. So actually, this component of the work, which was jointly published by myself and Dr. Arun Menon from IIT Madras, this was later updated by the global earthquake model, and that is currently being used to define the exposure model for India by the OpenQuake engine, by global earthquake model. So the typology part, it is very well done. What is the issue then? The issue is with respect to the vulnerability functions. So I've mentioned that there are 54 different typologies based on the construction material, type of lateral load resisting systems, number of stories, etc. But however, if you look at the vulnerability function side, you can see only 5 vulnerability curves here. Okay, there are 54 typologies, but 5 vulnerability curves. What you will realize here is that although the project has been successful in identifying different building typologies in the Indian context, it has not been very successful in defining appropriate vulnerability functions. The vulnerability functions shown here only account for the predominant construction material. That is, if it is a steel construction, it is assigned one vulnerability curve. If it's a reinforced concrete construction, it is assigned another curve, and so on. So regardless of what the lateral load resisting system is, regardless of the structural configuration, which is very important in dictating the seismic response, regardless of what the seismic design level is, what the quality of construction, etc. is, just based on the type of construction material, the typologies are being assigned a certain vulnerability curve. This is incorrect, because if you use just an average model for a whole set of building typologies, what you get at the end will not be representative of the vulnerability for each individual typology. You will get some average model which does not reflect reality for different typologies. Okay, so this is one area where significant research efforts are required, and this is one area where many of you can actually work on. Each of you can examine how different attributes such as structural system, configuration, compliance to seismic standards, compliance in the sense, is it a design building or is it a gravity design building? Is it a seismically designed building versus a gravity designed building? If it is a seismically designed building, to what level is it designed to? What is the effect on the vulnerability assessment? How does quality of construction and maintenance affect the vulnerability assessment? How does site topography affect the vulnerability assessment? So all of these are items which all of you can work on. You have different attributes and you have 54 different typologies which you can work on. So further studies are required to understand the impact of each of these attributes on seismic fragility and vulnerability. And I strongly urge all of you to read more on the subject, because this is an area that involves, that is closely related to practical implementation. It's not something theoretical, but it is something that that does not remain on a piece of paper, but which has to be translated to reality. So this is a very important area, a very booming area. So I just wanted to give you a glimpse of some keywords. I just wanted to introduce some keywords. That is it. I do not expect you to be a master of any of the things that I've mentioned in the past 1.5 hours by the end of the session. But the whole point was to just introduce you to some key terms which are important as far as this field is concerned, so that you can closely work on any of these things. So with this, I close the presentation. If you have any questions, I'll be happy to take them. I know it was a bit tiring presentation and a lot of advanced topics were introduced, but I think this is very essential, because this is not something which is taught to students within a classroom setting. So you will not get this in class. So this is something which you have to understand if you want to go for higher learning, if you want to develop your understanding of earthquake engineering. Particularly, I will strongly recommend that you break out of the shell of linear elastic analysis and graduate to nonlinear analysis, at least at the stage, at least at a postgraduate level. So thank you. If you have any questions, I'll take them now.
Thank you so much, sir. The session was very informative. We could gain a lot of knowledge about seismic analysis. Now the forum is open for discussions. Participants, you can either type your queries in the chat box or unmute yourself and ask your doubts. Participants, please.
Questions? I know the topic is a little advanced, but kindly go through the reference materials that have been provided. It will do a lot of good if you go through these concepts. I'm pretty sure, even though we have even faculty members attending this, I'm pretty sure that this will be new information to many of them, because this is not something which is typically taught. Even at most IITs, this is not something that is taught. Okay, so this is something which you can do use at a MTech project level or at a PhD research level, but this is something which is very important. So I think at the end of this, you are also required to take a MCQ test. So don't worry, the test is very easy. Although the topic was very advanced, the test is very easy. Okay, so I wish all of you the very best. If you don't have any questions,
sir, we have one question from Mr.
Sure.
Arun Krishna. Where we get peer database? Is that a software model or directly from Google?
Thank you for the question. Actually, peer database, if you just type peer ngvs2 database on Google, you will be able to access the website. It is a website. You can create a free account. Once you create a free account, then the first screen which you see will be the screen which I have displayed on my slide. So the first screen that you will see after you register will be the screen to specify the target spectrum. Okay, so the steps I have already included in my slide. To access peer, you just need to Google peer ngvs2 database. You will see the link. It will be the first thing to pop up. Just click on that, create a free account, and you can use the database to your advantage.
Thank you so much, sir. Any other questions? Hope there are no more questions. So once again, Rohan sir, thank you so much.
You're welcome. You're welcome. It's a privilege for me to also share whatever little I know with people who are willing to learn earthquake engineering. And although this was an advanced lecture, I hope it would have been useful at least to some of you. Please do make sure that you take the test. The test is pretty easy. Don't worry about it. If you have any queries, I don't know if I've shared my email ID in my bio, but if it's not there, I'll share it in the chat box. If you have any queries
Yes,
right
please.
now or in the future, you feel free to ask me, because I'm sure that you will have doubts in the future, because at an MTech project level, many people do pushover analysis, many people do nonlinear dynamic analysis. So somewhere you will get stumbled. I'll be happy to help you in case you have any queries. So all the best to the students as well as the faculty members. Thank you.
Thank you so much, sir. Participants, the feedback link is already shared in the chat box. Please complete it and submit by 11:15. And slides and recordings all will be shared to you later. Now we'll have a short break. Please rejoin back by 11:10 a.m. and we'll start our next session by 11:50. Thank you so much. Thank you, sir, once again.
Thank you, sir. Thank you, Dr.
Yeah.
Very happy to have you with us.
Thank you. Everyone, have a nice day.
Welcome back, dear participants, to the second session of the day. The session will be handled by Dr. Deepa Balakrishnan, Professor, Department of Civil Engineering, School of Engineering, Pusat, Kerala, on the topic earthquake-resistant construction techniques. Let me welcome Dr. Abhilasha PS, Coordinator of FDP, to introduce the speaker for the session. Ma'am, please.
Deepa Miss. Deepa Miss. I hope Deepa Miss is there. Please switch on your mic and camera, ma'am. Deepa Miss. Can you hear me, Miss? I think there's some issues. Let me make a call. Hello, ma'am. We are not able to see you, ma'am. Are you there? Is it an issue? Okay, please join. Please take your time. No problem, ma'am. We are waiting. No, ma'am. No need to share now. Okay, okay, sure. Please join. There is some network issue over there. We shall wait for it. Okay, so Mrs. Dibamis is here. So namaste everyone. Hope all of you had enjoyed our first session. And now moving on to our second session of third day Untitled FDP on recent advances in earthquake engineering. We have with us Dr. Diba Balakrishnan, Professor, School of Engineering, Cochin University of Science and Technology. And her topic is earthquake resistant construction techniques. Now, moving on to speakers' qualifications and all other details, she did her PhD from Cochin University of Science and Technology in the year 2009 and MTech in Structural Engineering and Construction Management and got third rank from Kerala University, and BTech also she was awarded with the distinction and she completed it from the same Kerala University itself, and her research thesis is numerical investigation on soil structure interaction of multi-story frames. And she executed different projects, and one is under TechCube 3, development of high-strength lightweight coconut shell aggregate concrete for structural applications. And other achievements are, she is an executive member of Indian Society of Systems for Science and Engineering, Cochin chapter, and she's also a life member of professional bodies like ISE, IGS, ICI, IEI, ISCT, and organizing committee member of Biennial Conference of Division Race since 2004. And she is a technical reviewer for many conferences like RACE, RASC, etc. She chaired the technical sessions for conferences like ICRACE, RASC, etc. and has acted as a member of the syllabus committee for NORCA Roots. She also coordinated a 3-day workshop on earthquake engineering for engineers and architects along with the district administration. She coordinated a STTP on advancements in concrete technology and special concretes under TechCube. She has acted as reviewer for KSCTC project for funding and also acted as a resource person for expert lecture on engineering education. Her experience is teaching 25 years and research it is 15 years and 1 year industrial experience also. And her areas of interest, that is interaction studies on structures, development and studies on special concrete, performance-based design of structures, and she got publications total of 29 in international journals, 7 other, international conferences, 12 other, national conferences 5, and 5 book chapters. So that is about our speaker. So warm welcome, dear Dr. Diba Balakrishnan Madam to the platform, and we are waiting anxiously to listen from you. Welcome, ma'am. You can share your screen now, ma'am. I shall stop my sharing. Okay, ma'am. Diba, ma'am. Please switch on your camera. Yes, screen is visible now, ma'am. And please switch on your mic and unmute yourself. Is there any technical issue, ma'am?
Am I unmuted now?
Yeah, no, we can hear you now, ma'am. But we are not able to see you. Please switch on your camera also.
Okay.
Yes, yes, yeah, now it's perfect. Yes, yeah. Yes, ma'am. You can put in slideshow mode.
Yeah. Okay, Abhilasha. Thank you for the introduction. And I think thanks to Vidya Academy of Science and Technology for this opportunity. So let me move to my presentation. So maybe I will start.
Yes, ma'am. Please start.
Okay. So good morning, all the participants. So this is today's second session. So here we will discuss certain technologies or techniques available in the earthquake resistant construction field. So before starting a small introduction to this, the world is witnessing urbanization at an unprecedented pace, which is expected to further accelerate, and India is anticipated to lead this growth India's mass urbanization is predicted to make it the third biggest construction market by 2030. A well-functioning modern infrastructure is central to economic development and to the quality of life. From the roads and railways needed to transport people and goods, to the power plants and communication networks that underpin the economic and household activity, to the basic human need for clean water and sanitation, infrastructure matters to people and businesses everywhere. And in this present scenario, where indiscriminate constructions are going on, strikes the disasters. Among all the natural disasters that take place, earthquake causes maximum loss of life and limb. Tremendous loss of property, especially buildings, is caused, leaving a large mass of population shelterless. Buildings are badly damaged, as this requires demolition. A severe earthquake can have very damaging consequences upon a region's development and economy. We are heavily dependent upon the civic amenities like water supply, electric power supply, drainage, etc. Earthquake can disturb the civic amenities in a major way. Lifeline facilities like hospitals, healthcare centers, etc. have a major role in natural catastrophe like earthquake. Losing them during an hour of need is disastrous. Loss of heritage buildings is another cause of concern. Heritage connects us with our ancestors and gives a sense of pride and belongingness. Damage of heritage buildings can make us rootless. The new structures can often be rebuilt, but the loss of heritage is a huge one. Their reconstruction is difficult, as well as the very sense of it being built historically is lost forever. The partially damaged buildings are like ugly scars and deformities with which we are forced to live. Beautifully planned towns and even major cities can be turned into mounds of debris. Both physical and psychological damage are caused, having long-lasting implications for the inhabitants. And as for the casualties, what to say, earthquakes don't kill people, but buildings do. It has been observed from many past earthquakes that the damage to buildings is unreasonably high in India compared to many other countries of the world for similar level of ground shaking. Hence, there is an urgent need to understand and address the risk in housing and infrastructure sector in India, so that future loss of life and property during such a calamity can be minimized. As for the aim of the earthquake-resistant design, engineers do not attempt to make earthquake-proof buildings that will not get damaged even during rare but strong earthquake. Such buildings will be too robust and also too expensive. Instead, the engineering intention is to make buildings earthquake-resistant. Such buildings resist the earthquake ground shaking, although they may get damaged severely, but will not collapse during a strong earthquake. The safety of people and contents is assured in earthquake, and a major disaster is avoided. This is a major objective of the seismic design codes throughout the world. Keeping in line with this design philosophy accepted throughout the world, Indian Standard Code IS 1893 gives the philosophy of earthquake design as to ensure that structures possess at least a minimum strength to withstand minor earthquakes without damage, resist moderate earthquakes without significant structural damage, and that structures withstand a major earthquake without collapse. Even though as such, this statement is missing from the latest version. And to the aim of the earthquake resistant construction, severity of a ground shaking at a given location during an earthquake can be minor, moderate, or strong. Relatively speaking, minor shaking occurs frequently, moderate shaking occurs occasionally, and strong shaking rarely. So, should we design and construct a building to resist that rare earthquake shaking that may come only once in 500 years or even once in 2000 years at the chosen project site, even though the life of the building itself is only 50 or 100 years? Since it costs money to avoid additional earthquake safety in buildings, a question may arise. Can we do away with the design of buildings for earthquake effects? Or shall we provide it? Should we design the buildings to be earthquake proof, wherein there is no damage during the strong but rare earthquake shaking? Clearly, the former approach can lead to a major disaster, and the second approach is too expensive. Hence, the philosophy of design and construction should lie somewhere in between these two extremes. And the philosophy of construction is the idea of construction is the fabrication of a building or structure is able to withstand sudden ground shaking that is characteristic of earthquakes, thereby minimizing the structural damage, human death, and injuries. With this in mind, today we will have a look at the effect of earthquake on structures and discuss about the construction techniques, both conventional as well as unconventional, and recent developments in this field, and then summarize. So before we move into the construction techniques, you have to understand the earthquake first. An earthquake is a sudden rapid shaking of earth caused by the sudden release of strain energy stored in rocks. Energy released from this source travels through the body of the earth as well as through the surface in the form of pure waves or love wave or Rayleigh wave. And each of these waves have different modes of transmission, be it the translational mode or the rotational or elliptical mode. Energy released from the source of disturbance inside the earth is transferred to adjacent land and water and vibrate. Random motion in earthquake shaking occurs in all directions. Therefore, buildings and structures designed to resist earthquake shaking must have strength to withstand shaking from all directions. A normally designed reinforced concrete building, the structural members like the walls, columns, etc. experience only vertical loads or the gravity loads, vertical or gravity loads. But during an earthquake, the earthquake forces are developed in both the orthogonal horizontal directions as well as in the vertical directions. However, the maximum amplitude of earthquake vibration in the vertical direction is usually less than that in the horizontal direction. Hence, our buildings have proved capable of withstanding vertical acceleration efficiently. It's the horizontal accelerations that cause damage to buildings, and this must be designed for. These horizontal forces causes lateral and shear loadings, which results in tensile and torsional forces on the structural elements. And these forces result in high stresses at the building's corners and throughout the various joints. Now, earthquake causes shaking of the ground. A building resting on it initially experiences a motion at its base. Even though the base of the building moves with the ground, the top has a tendency to stay in its original position. But since the walls and columns are connected to it, they drag the roof with them. This tendency to continue to remain in the previous position is known as inertia. In the building, since the walls or columns are flexible, the motion of the roof is different from that of the ground. The inertia force experienced by the roof is transferred to the ground via the columns or walls and then to the foundations. It is this inertia force that is the most important force generated during the earthquake, and it's proportional to building's acceleration during the ground motion. And because of the complex nature of the earthquake ground motion, the building tends to vibrate back and forth in varying directions. Now, another type of, or another point which is of importance here is that in addition to displacing towards the side under the action of the ground motion, the building is also shown to change its shape. Here we can observe the shape changing from rectangular to a parallelogram. That is, it is deforming. The primary cause of earthquake damage to buildings is the deformation which the building undergoes as a result of inertial forces acting upon it. Suitable construction methods are required to ensure that proper design objectives for earthquake resistance are met. Construction methods can vary dramatically throughout the world, so one must be aware of local construction methods and resource availability before concluding whether a particular earthquake resistant design will be practical and realistic for that region. Now, earthquake effect on a building is dynamic in nature. Hence, it is the dynamic properties of the structure like mass, strength, stiffness are the ones that decide its performance during earthquake. And suitable construction techniques that suit the requirement is to be chosen. These techniques are applicable to seismic retrofitting also to improve the efficiency of a building damaged during earthquake. And today we will divide these construction techniques mainly consists of seismic resistant construction, seismic isolation techniques, and seismic vibration control. And before employing any technique for any building construction, the first step is a proper site selection. For a seismically active region, more care has to be given in the selection of site. So, in such localities, buildings should be sufficiently away from steep slopes or filled up soil. And if it is unavoidable, use raft or pile foundation. Now, for the structures, the earthquake resistant design mainly depends on its configuration, the strength, stiffness, ductility. These are properties inherent to the building. The behavior of a building during earthquake depends critically on its overall shape, size, and geometry, in addition to how the earthquake forces are carried to the ground. Hence, at the planning stage itself, architects and structural engineers must work together to ensure that the unfavorable features are avoided and a good building configuration is chosen. In general, buildings with a simple geometry in plan have performed well during strong earthquakes. Buildings with reentrant corners like this, those of U, this T, or cross-shaped plans have sustained significant damage. The bad effects of these interior corners in the plan of buildings can be avoided to some extent by making the buildings separated into parts. So, as far as possible, avoid irregular plans and asymmetry in the building, because that can lead to torsion or twisting effects happening in the structure during an earthquake. Likewise, the vertical layout of the building is also important. The earthquake forces developed at different floor levels in a building need to be brought down along the height to the ground by the shortest path. A deviation or discontinuity in this load transfer path results in performance of the building. Buildings with the vertical setbacks, this is a common configuration. Many hotel buildings will be having this type of configurations, or other commercial buildings also, nowadays high-rise buildings with a few stories wider than the rest. And this causes a sudden jump in the earthquake forces of discontinuity. The plan is simple, but the columns and walls are not equally distributed in plan. Buildings on slopy ground, they have unequal height columns along the slope, which causes ill effects like twisting and damage in the shorter columns. Buildings with columns that hang or float on beams at an intermediate story and do not allow or do not go all the way to the foundation have discontinuities in the load path. Stress concentrations happens at such joints and corners and can lead to severe damage. Some buildings have reinforced concrete walls to carry the earthquake load to the foundation. Buildings in which these walls do not go all the way to the ground but stop at an upper level are liable to get severely damaged during earthquakes. This happens for buildings with a weak or flexible story on the ground stories or in the ground floors. So, sudden change of lateral stiffness should be avoided, as well as large overhangs and projections are also to be avoided. Now, the seismic inertia force generated at the floor levels are transferred through the various beams and columns to the ground. These main structural elements in the earthquake resistant buildings need to be built with ductility in them. Such buildings or the ductile buildings will have the ability to sway back and forth during an earthquake and to withstand earthquake effects with some damage but without collapse. Ductility is one of the most important factors affecting the building's performance. Thus, earthquake-resistant design strives to predetermine the locations where damage takes place and then to provide good detailing at these locations to ensure ductile behavior of the building. So, it's necessary that the correct building components need to be made ductile. The failure of a column can affect the stability of the whole building, but the failure of a beam causes only a localized defect. Therefore, it is better to make beams to be ductile weak links and than that of the columns. And this method of designing RC buildings is called the strong column weak beam design. We are predetermining where the failure can happen. Okay, and initiate designing in such a way that failure happens in the beams. Now, the importance of horizontal bands. Horizontal bands are the most important earthquake-resistant features in masonry buildings. The bands are provided to hold a masonry building as a single unit by tying all the walls together. Depending upon their location, there are many bands like the roof band or the lintel band or the plinth band. And in pitched roof construction, there is the gable band also. All this named after their location in the building. Of this, the lintel band ties the wall together and reduces the unsupported length of the walls and thereby improves the stability in the weak direction. Now, during the 1993 Lateral earthquake in central India, the intensity of shaking in Killari village was 9. Most masonry houses sustained partial or complete collapse. There was one masonry building in the village which had a lintel band which had sustained the shaking very well with hardly any damage. And this is a visual example of the importance of providing lintel bands in masonry construction. Walls and columns are the most critical elements in transferring the inertia force. But in traditional construction, floor slabs and beams receive more care and attention during design and construction than walls and columns. Walls are relatively thin and often made of brittle material like masonry. They are poor in carrying horizontal earthquake inertia forces along their direction of thickness. And failure of masonry walls have been observed in many earthquakes in the past. The joints of walls are very critical. And strong construction joints are critical in a building that will withstand the shear load due to earthquake. And since stress is concentrated at the joints between the walls, it is important that all the joints be properly prepared and reinforced. And concrete joints must be properly compacted and anchored in order to obtain maximum strength. Of the three components of a masonry building, the roof, wall, and foundation, walls are the ones which are most vulnerable to damage caused due to the horizontal forces during an earthquake. A wall topples down easily if pushed horizontally at its base or horizontally in a direction perpendicular to its plane, which we call the weaker direction, but offers much strength or greater resistance if pushed along its length, which is the strong direction. To ensure good seismic performance, all the walls must be joined properly to the adjacent walls. In this way, the walls loaded in their weak direction can take advantage of the good lateral resistance offered by walls loaded in their strong direction. So this is especially very important in the case of unreinforced masonry joints also. When all the joints are tied together well, the building will act as a single integrated unit, enabling the forces of an earthquake to be transferred from one section to the next without catastrophic failure. An improvement to this type of masonry construction is the confined masonry construction. This construction typically consists of a strip foundation in masonry, a reinforced concrete plinth beam, masonry walls in brick or concrete block units built on top of this plinth beam, small RC vertical and horizontal confining elements built around this masonry walls, then RC floor and roof slabs built monolithically with the confining elements. These horizontal and vertical confining elements are called the tie beams and tie columns. Confined masonry construction has a mandatory plinth beam on top of the plinth masonry. This technique is very good for low and medium rise houses in seismic areas. And this figure shows a 4-storied house constructed in Chile with a confined masonry system. The construction of this confined masonry building with RC confining elements, this involves making the masonry walls in small panels, each of which is confined on all 4 sides by vertical as well as horizontal RC elements. Concrete is poured in these vertical and horizontal confining elements after the walls are built. RC confining elements hold the masonry in place and improve the integrity of the house during seismic shaking. These are essentially load-bearing structures because the masonry walls carry both gravity and earthquake-induced lateral forces. And this type of construction has enhanced stability and strength compared with ordinary masonry construction, and are very economical when we are comparing this with the framed construction. So very suitable for medium rise buildings in earthquake prone areas compared to reinforced concrete moment resisting frame constructions. Now coming to the lateral load resisting systems. These are the systems that designers choose from when designing structures to resist horizontal loads. Can be the shear wall construction or adding bracings or adding infilled walls to framed construction. One of this system must be present in each orthogonal direction. If, for example, shear wall is used in one direction, then the designer can choose any other method in the opposite direction that suits the planning and architectural concept. So for seismic resistance, the immediate answer is shear wall. These are reinforced concrete walls, which extends from the foundation to the top. The points to be noted in the construction of shear wall is that they have to be provided symmetrically, because the shear walls provide a lot of strength and stiffness to the building in the direction of their orientation. And they carry large horizontal earthquake forces, which can lead to large overturning moments. And therefore, proper foundation has to be provided for them. And this has to extend from the foundation till the top. Usually 150 to 400 mm thickness is provided for the shear wall. And the cross sections can be rectangular or L-shape, U-shape and all. Even the thin-walled RC shafts around the elevator core of the building can act as shear wall. Reinforcements are to be provided in 1 or 2 layers, both in the horizontal as well as in the vertical direction. Another method is providing bracings. These are moment resisting frames with the braces added. The connection between the braces and the frame can be rigid jointed or pinned. Depending on the orientation of the bracing, it can be X bracing or chevron bracing or eccentrically braced frame. They are very flexible and the loads are transferred primarily by the axial force in the members. And have the advantage of higher strength and stiffness and openings for natural light, and adds only less weight to the structure, and can be used as a retrofitting technique also, that is for the repair of structures which are damaged during an earthquake. In such cases, the work can be performed with the prefabricated elements, and hence the disturbance to the occupants may be minimized. And there are certain limitations for this. That is, the original architecture feature of the building is altered. And it's also very sensitive to construction errors. And that can lead to the failure of the entire bracing system because of the reduction in the member capacity. Therefore, this requires skilled labor. Another important method which can easily improve the lateral stiffness and stability of the frames is by adding infill walls. This method is also applicable for repair or retrofitting after a seismic event. So this is an effective and economical method for improving strength and reducing drift in new or existing frames. Adding masonry units or filling the space between the frames or members of the frames by masonry or any type of blocks. A relatively strong masonry infill may result in the failure of columns of the existing frame. This is one thing that is to be taken care of. But we don't need failure of the columns. The masonry has to be properly anchored to the frame to improve the performance. And with proper anchorage, it is possible to force failure in the masonry and to prevent the premature column failure. That is a certain thing to keep in mind when going in for infill walls. And this is not the same as that of the confined masonry. This is adding masonry infills to an already existing framed construction. Now, reinforced concrete frame buildings are becoming increasingly common in urban India. Many such constructions in recent times have a special feature. The ground story is left open for the purpose of parking. Such buildings are often called open ground story buildings or buildings on stilts. The presence of walls in the upper stories makes them much stiffer than the open ground story. Thus, the upper story move almost together as a single block, and most of the horizontal displacement of the building occurs at the soft ground story itself. This can be avoided by covering up portions of the soft ground story. It's not possible to entirely cover up the open ground story if the purpose of it is for car parking and all, but portions of this can be covered, which will improve the earthquake resistance of the building. For this, we can make use of any of the three methods which we have seen. We can provide the shear wall, or bracings can be provided, or it can be by providing brick infills. One thing to keep in mind when we are doing this is that whatever we are providing, provide that symmetrically. So, earthquake resistant buildings design depends upon providing the building with the strength, stiffness, and inelastic deformation capacity, which are large enough to withstand a given level of earthquake generated force. This is generally accomplished through the selection of an appropriate structural configuration and careful detailing of structural members, such as beams and columns, and the connections between them. But more advanced techniques for earthquake resistance is not to strengthen the building, but to reduce the earthquake generated forces acting upon it. So the advanced techniques are base isolation techniques, as well as the usage of energy dissipation devices. Base isolation aims at reducing the horizontal seismic forces. And this is a relatively cheaper and powerful method of seismic rehabilitation of buildings also. A typical base isolation system consists of rubber bearing located at the base of the building, just below the first floor under the columns of shear walls. These rubber bearings consist of laminated layers of rubber and steel plates strongly bonded together during the vulcanizing process. So this bearing has a top and bottom and in the middle there is a lead core. We'll see what is the purpose of providing this lead core. So this type of bearings are designed with vertical stiffnesses almost 300 to 1000 times that of the horizontal stiffness. Such a system increases the first natural period in both horizontal direction, and the response acceleration decreases accordingly. See, these base isolations are provided at the base of the building and they are supported by a series of bearing pads and are placed between the building superstructure and the foundation. And this bearing is stiff and strong in the vertical direction, but it is flexible in the horizontal direction. And a variety of different types of bearing pads have now been developed. It can be the sliding plate bearing, or sliding cum rocker bearing, or roller cum rocker bearing, or the elastomeric bearings. So the choice of or the type of bearing for a particular structure depends on the type of vibrations that this type of bearings are expected to take. Now, this shows the effect of earthquake ground motion on a conventional fixed base building and a base isolated building. The fixed base building undergoes displacement in the direction opposite to the ground motion. The ground movement is shown. So the building is undergoing displacement in the direction opposite to the ground movement. The building's displacement in the direction opposite to the ground motion is due to inertia. But due to the complexity of the earthquake ground motion, the building's displacement is not limited to one direction alone. It vibrates back and forth. In addition to displacing, the conventional fixed base building deforms by changing its shape. The rectangular shape now changed to a parallelogram. The primary cause of earthquake damage to buildings is this deformation which the building undergoes as a result of the inertial forces acting on it. And what happens in the base isolated building? Under the action of this ground movement, it is the isolation bearings that is taking the displacement, whereas we are not observing any deformation happening to the building. So the base isolated building escapes the deformation and damage. And this implies that the inertial forces acting on the base isolated building have been reduced. And experiments and observations of base isolated buildings in earthquakes have been shown to reduce the building acceleration to as little as 1/4 of the acceleration of the comparable fixed base building. So the earthquake forces generated in this building is getting reduced to almost 1/4 by the inclusion of this base. As we have noted, the inertial forces increase and decrease proportionally as acceleration increases or decreases. Acceleration is decreased because the base isolation system lengthens a building's period of vibration. That is, the time it takes for the building to rock back and forth is increased. And in general, structures with a low period of vibration tend to reduce the acceleration, while those with the short periods tend to increase or amplify the acceleration. And since these are highly elastic, the bearings, the rubber isolation bearings don't suffer any damage. Now, as for the mechanism by which the energy is dissipated in the bearing, we have seen that there is a lead plug in the middle of the bearing. And this lead plug in the middle of the bearing experiences the same deformation as that of the rubber. However, it generates heat. Or in other words, the lead plug reduces or dissipates the energy of motion, that is kinetic energy, by converting it into heat, and thereby reducing the energy entering in the building. Thus, it helps to slow and eventually stop the building's vibrations sooner than would be the case. In other words, we can say it dampens the building's vibration. This is the mechanism happening in the bearing. So this is how the bearings dissipate the energy. As for the advantages of using bearings, this gives better protection against due to decrease of shear. And since the overall earthquake load on the structure is reduced, no additional reinforcement is needed in the superstructure. And the foundation system will not need extra reinforcement to resist the overturning moments. This is what we have seen in the case of shear walls. And if it is used for retrofitting, that is after an earthquake event, to repair damaged buildings, there will be least interruption of the building activities and least amount of temporary work is required. And the usual damping of 5 to 10%, the structural damping increases up to 20% with the addition of dampers. Now, the second method is by using supplemental damping devices. This second major new technique for improving the earthquake resistance of building also relies upon damping and energy dissipation, but it greatly exceeds the damping and energy dissipation provided by the lead rubber bearings. As we have said, a certain amount of vibration energy is transferred to the building by equipping a building with additional devices which have high damping capacity. We can greatly decrease seismic energy entering the building and thus decrease building damage. Our buildings have an inherent ability, even though limited, to dissipate or damp this energy. This is what we call the structural damping. And to overcome, or in those cases, or in seismically active region where the earthquake energy transferred to the structures are coming more than the capacity of the structural damping, it becomes necessary to provide this type of supplemental damping devices. And a wide range of energy dissipation devices have been developed and are being used in real buildings nowadays. So equipping a building with additional devices which have high damping capacity greatly decreases the seismic energy entering the building and thus decreases the building damage. And these damping devices can be viscous dampers, where the energy is absorbed by silicon-based fluid passing between piston cylinder arrangement. What can be the friction dampers, wherein the energy is absorbed by surfaces with friction between them rubbing against each other. Or it can be yielding dampers, where the energy is absorbed by the metallic components that yield. So the common types of dampers that are used. Now this dampers consists of a stainless steel piston divided into two chambers by the piston head. A compressible hydraulic fluid, usually silicone oil, and then there is an accumulator for smooth fluid circulation. Fluid viscous dampers work based on the principle of dissipation of energy because of the fluid flowing through orifices. Now, as the piston moves from left to right, from the left chamber to the right chamber, or from this right chamber to the left, fluid flows from one chamber to another chamber through the orifice. This movement of fluid from a larger area to a smaller area, or from a smaller area to the larger area, results in dissipation of energy because of head loss. The damping force of the damper is proportional to the pressure difference across the piston head. Fluid viscous dampers are available in wide ranges, and they can operate in ambient temperature ranges of -40 degree to 70 degree. A variety of dampers are available. And as for the installation of this type of fluid viscous dampers, the damping devices are usually installed as part of bracing system. This figure shows one type of damper brace arrangement with one end attached to a column, and on the other end it's attached to a floor beam. Primarily, this arrangement provides the column with additional support. Most earthquake ground motions, it's in the horizontal direction. So it is the building's columns which normally undergo the maximum displacement related to the motion of the ground. And by connecting this building column with the beams by means of this type of raised dampers, it provides additional support to the column. One of the newer invention, it's not fully in use, still in the experimental stage. Here, when an earthquake strikes, the system of steel frames in the building's core and exterior dissipates the energy. These frames are free to rock up and down within fittings fixed at their bases. Steel tendons made of twisted cables run the entire length of each cable, the entire length of each frame, keeping the frames from moving so much that the building could shear. When the earthquake stops, these tensile tendons pull the frame back into the shoes at their bases, returning the building to its upright position. So that's why the technology is called keeping the building upright. Now, a research team led by the Stanford and University of Illinois successfully tested this structural system And it has been observed that this can hold buildings together even through an earthquake of magnitude 7, and even pulls it back upright on its foundation when the earthquake shaking stops. So, experimental study is still going on in Japan's Hydro Earthquake Engineering Research Center. Another latest innovation in this is the use of spherical sliding isolations. It uses bearing pads that have a curved surface and low friction materials similar to Teflon. During an earthquake, the building is free to slide both in the horizontal and vertical direction, and it will return to its original position after the ground shaking stops. It's the spherical sliding isolation. Now, as for some examples where these techniques are being used. And the most notable one in this is the Sabiha Gökçen International Airport. This is one of the 2 international airports in Istanbul, Turkey. And the peculiarity of this place is that it is located near the North Anatolian Fault, which is a very active seismic fault. Here, for this airport, the whole terminal building sits on a platform that is to a very high degree isolated from the ground below. So this enabled the team of structural engineers to design the terminal almost as though it were situated on a non-seismic location, and to include features such as large spans and all, because the platform and the isolation methods mean that the violent lateral ground movements will scarcely affect the structure. Even during very violent earthquakes, there won't be any effect on the whole of the airport structure. It's totally isolated from the ground. And the example of mention is the Trans-America Pyramid, the height of which is 260 meters. And this is in San Francisco, USA, California. And this is also important. Why? Because of its proximity to a major fault line like the San Andreas and Hayward faults. The building's concrete and steel foundations are designed to move with any earthquake, and these foundations reach as far as 52 feet deep. And this base allows for stability and the absorption of shock waves. And this was all put to test in 1989 during the Loma Prieta earthquake of magnitude 6.9. Although the building was reported to have swayed by about 30 centimeters at the top to either side during the earthquake, there was no structural damage to the building. And this shows a seismic retrofitting adopted for another building in Glendale. And here we can see elevated or bearings. Bearings are provided. And see, the whole structure is on an elevated building foundation. And this rests on high damping rubber bearings. Therefore, during earthquakes, this is also located in a highly seismically active region in California. And what happens during earthquake is that the bearings will take up the moments, and the superstructure is spared of any damage. As for the usage of this technique in India, base isolation technique was first demonstrated after the 1993 Killary earthquake. 2 single-story buildings, one school building and another shopping complex building in the newly relocated Killary town were built with the rubber base isolators resting on hard ground. And both of these were brick masonry buildings with a concrete roof. Another example to say is about the General Hospital in Puch. This hospital was badly damaged during the 2001 Bhuj earthquake. The structure collapsed, 150 or more casualties, including the patients, the doctors, hospital staff, all were severely affected during the earthquake. Later, the hospital was reconstructed. And when it was reconstructed, actually it's not the old hospital reconstructed at the same location, but a new hospital has been made for the Gujarat General Hospital, which, and here at the basement, base isolators are provided to take care of any earthquake loads happening. We can see the isolators being provided at the basements. And another example is the La Gardenia Towers in Gurgaon. The construction of this happened in 2001. And here, frictional dampers were being used. This is an 18-story apartment building. And the Paul friction dampers, that's the trade name, because Paul Dynamics is the one which undertake the construction. Dampers in steel bracings were used. The earthquake resistance and damage control potential of the structure has increased dramatically with the usage of this. During a major earthquake, the friction dampers slip at predetermined load before yielding occurs in the members and dissipate a major portion of the seismic energy. Hence, total dependence on ductility is avoided, and the structural elements remain generally elastic without damage. So a well-designed and constructed RC building is expected to collapse only when an earthquake measuring 7.5 or higher on Richter scale takes place. So we have seen 3 major methods of earthquake-resistant constructions. By incorporating ductility or improving the seismic resistance of the structure as such, or by adding seismic isolation, or by adding in some seismic vibration control mechanism. So comparing these 3, in the seismic isolated structure, the earthquake energy is absorbed by the bearings. And in the vibration controlled structure, the energy is absorbed by the vibration control mechanisms or the dampers that are provided in the structure. Okay. And in the seismic resistant structures, the overall structural construction is improved by imparting ductility to the various structural elements, and the structure is made to perform well during an earthquake. But comparing these 3, by incorporating basic seismic isolation to the structure, the seismic load on the structure is very much decreased compared to seismic resistant structure. Here, the seismic load transferred from the foundation to the structure is decreased by the incorporation of seismic isolations at the base. Therefore, as such, we don't need additional reinforcements and all in the superstructure. Okay. So of the three, this is the one that performs best during an earthquake. And it's only the initial cost of providing these dampers that's there. And even when the dampers get damaged, we can always replace that. So it's a best method for seismic construction as well as retrofitting also. So with this, let me stop my presentation here. Some of the references. And thank you.
Thank you so much, ma'am. The session was very informative. We could gain a lot of knowledge about earthquake resistant design, shear wall construction, base isolation, damping devices, and a lot more. Now the forum is open for discussions. Participants, you can type your queries in the chat box or you can unmute yourself and ask questions. Participants, please. Ma'am, we have one question in the chat box. Let me read it out.
Yes.
The question is from Mr. Panindranath, requesting to send the presentation. Okay, the presentation and recordings will be shared with you later. One question is there from Mr. Arun Krishna, where we can select the position of shear walls. How can we select the position of shear walls?
Oh, actually, first thing to note is that whether we require shear wall or not. So for an efficient and proper shear wall, we have to ensure that this is an RC shear wall, reinforced concrete wall, which extends from the foundation till the top, sufficiently thick, and with the proper reinforcements. So, and when we are providing such type of walls on all the four sides of a building will be very uneconomical, because when we are providing shear walls, we have to ensure the symmetricity also, because by providing shear wall only on one side, that will improve the strength there, but can lead to twisting, because the remaining portion of the building or the orthogonal directions are not that stiff and strong, therefore can lead to twisting. Therefore, that's why it said that shear walls are to be provided symmetrically.
Okay, thank you, ma'am.
One second more. If you have already decided that you are going to provide shear wall, then it can be either in the inside or outside of the building. That's why I said even the lift core of the building will also act as shear wall.
Okay, thank you so much, ma'am. One more question from Ms. Adira Raghunandan. Is there any disadvantages for base isolation?
Disadvantages for base isolation as such, not much major disadvantage. See, it's that maybe after a major earthquake shaking and all, this bearing, this can get damaged, rubber bearings can get damaged and all, but it's easy to remove that and replace it. Only the initial expense is there. Okay, so it's a very advantageous method.
Okay, thank you, ma'am. Next question is from Ms. Anvita Sinha. What type of damper will be suggested for two-story timber structure in seismic zone 5 in Kashmir?
Kashmir. See, we have seen that it can be the friction dampers, or it can be that viscous dampers which are being used. If at all you are sure that there should be dampers provided there. Okay, two-story structures there. In Kashmir, just like that, the confined masonry, they have an indigenous particular method for protecting their walls and all. So being two-story building, if at all it's necessary, only you have to go for providing extra dampers. So friction dampers or viscous dampers will be suitable.
Thank you so much, ma'am. Next question is again from Ms. Adira Rathnandan. Is there any difference between earthquake-resistant building and earthquake-proof building?
Yeah, yes, there is. Earthquake-proof building meaning those earthquake which will try to resist the earthquake totally, but that's not our idea. If we want to make a building that will perform 100% against an earthquake, means that will be going in for heavy detailing of reinforcements, incorporating ductility to a very large extent, and things like that. Which will be very uneconomical. As we have seen, the design earthquake may come or may not come during the life of that structure. But in earthquake resistant buildings, what we are trying to do is that just like the aim of the earthquake resistant design, it's the inhabitants we are worried about. So even during a moderate earthquake or major earthquake, we should be able to do the evacuations and save the inhabitants, and the building may suffer some damages, which maybe we will be able to repair later. In some cases, it becomes necessary to discard the building or demolish it.
Thank you, ma'am. Next question is from Ms. Arya Sudhir. How expensive is base isolation?
Base isolation is definitely expensive, but when compared with the expenses for doing earthquake resistant design for a very high multi-story building, by improving its the reinforcements or providing extra reinforcements to improve the ductility and all, compared to that, the base isolation is cheaper.
Thank you, ma'am. And we have one more question from Ms. Adira Rathnandan. What type of buildings are very susceptible to earthquake?
What type of buildings, meaning usually the construction technology or the methods of construction which is used in different parts of the world. If we say particularly in India, we think that most of the regions are not seismically active, so we don't care much about the lateral loads in our design. So, but what happens during earthquake is that the lateral load resistant capacity of the elements are put to test. So if it is regular masonry buildings, they won't sustain these lateral loads. Therefore, understanding the seismicity of the region, we can improve it by going in for confined masonry type of constructions. And for the reinforced concrete buildings also, we cannot totally say they are earthquake proof and all, or earthquake resistant. See, if you are designing it based on the IS 456 or standard RC design codes, in that not much importance, or it's not leaning much towards the lateral load resistance. So if it is that's why a separate code is there for the earthquake design, and the detailing of which has to be done based on IS 13920, the special detailing code for earthquake resistance. So there is difference between the design philosophy adopted for both, and the detailing. So particularly, we cannot say simply masonry buildings will not perform or the RC buildings will not perform. Okay, that depends on how both of these are designed and constructed.
Thank you so much, ma'am. Next question is from Ms. Ashwati EB. Is it possible to retrofit existing buildings with base isolation?
Yeah, very much possible. That's a very ideal and good technique for retrofitting existing buildings.
Madam, good afternoon, madam. This is Manindra from Vizag.
Yes, sir.
Madam, you have shown various damping, what we call damping equipments, no, madam, like friction dampers, viscous dampers.
Yes.
So my doubt is, how could we, how could we give damping ratio for the damper, madam, while we are dealing with softwares?
How to give damping ratio for the dampers?
Yes, madam. Is there any material available for damping ratios for all the dampers, various dampers?
Sir, many of the cases, these dampers can be made specifically for the, depending on the need of the client, depending on the seismicity of the area and all. Maybe we will have to find out how much is the damping to be provided for a particular damper. Many of these agencies supplying the dampers, they are very specialized in this. Only thing is that we have to give the specifications and they will give us the dampers according to this specification. It's not that dampers are available with the, say, by damping ratio, you may mean if it is 0.3 or 0.5. Just like that, that value we have to arrive from the seismic design for the particular region and the building you are designing or the structure you are designing. We can back calculate and find out the value of the damping ratio. Is it okay? I don't know from where we cannot simply take the value as such from anywhere. But if it is a particular type of damper you are taking, maybe we can take it from their catalogs and all.
Yes, madam. Actually, 2 to 5% will be there, madam. Like for RCC, in code,
structure, that is the structural damping.
But my doubt is when we inserted external damping with fluid viscous dampers or friction dampers,
yes,
the damping ratio will get
structural damping will be improved.
Improved, ma'am. So I'm doing on that particular work, madam. How much damping was improved? How much percentage it will be compensated with damping? I'm working on it, madam. If any material available on it, then it will be helpful to me.
As such, what you can do is that you can run the analysis with both for both the cases, with and without the dampers, and you can see the responses and the variations.
Yes, madam. So we can we can find out the difference, how much it compensated actually. That's it,
yes,
ma'am.
Yes.
Yes. Thank you, madam. Thanks a lot.
Thank you.
Participants, any more questions? Hope the questions are over. Thank you so much once again. Now the slides and recordings will be shared to all the participants later. Feedback link is already shared in the chat box. Please complete it and submit by 1:15 p.m. today. And before that, one more note to the participants. You need 80% attendance and 60% score to receive the participation certificates from AICTE Atal portal. And at the end of validity function, you will have one more feedback link in which you will have to attend a final exam. In that also, you need 60% score. Okay, now we'll have lunch break and rejoin back by 1:50 p.m. We'll start the third session by 2 p.m. Thank you so much.
So, ma'am, thank you so much for accepting our invitation and joining with us today. Very happy to have you with us. Thank you, ma'am. Thank you.
Thank you, Abhilasha and team, and thank you, participants. Okay.
The participants have your lunch and join back sharp 1:55 p.m. Okay, thank you.
Good afternoon to one and all. Welcome, dear participants, to the third session for the day. The session will be handled by Dr. Sajid A.S., Associate Professor, Department of Civil Engineering, NIT Calicut, on the topic, Saline Features of Recent Earthquake Codes and Design of Special Structures. Let me welcome Dr. Abhilasha P.S., Coordinator of FDP, to introduce the speaker for the session. Ma'am, please.
Namaste. Good afternoon, everyone. Let me share my screen. Okay, so today we have with us Dr. Sajid A.S., Associate Professor, Department of Civil Engineering from NIT Calicut. And his session is Salient Features of Recent Earthquake Codes and Design of Special Structures. His educational qualifications, he completed his PhD in Structural Engineering from NIT Calicut in 2012 and ME Structural Engineering from PSG College of Technology, Coimbatore in 2001 and BTech in Civil Engineering from College of Engineering, Trivandrum in 1998. And his teaching experiences, he worked as faculty in Department of Civil Engineering, NIT Calicut, starting from 2002 till date. And his R&D projects are, that is, he worked as co-investigator in the R&D project, use of Coir-Pitford Airport Soft Ground Arrestor System, sponsored by Coir Board MSME, Government of India. And to his account, there are 18 journal papers, 14 international and 3 national conference papers. And he's actively engaged in the consultancy activities. And he worked as reviewer for Journal of Vibration and Control, SCGE Publishing, and reviewer as a reviewer for Journal of Marine Science and Application, Interview Publishing, and guest editor for the proceedings of CCON 2019, Structural Engineering and Construction Management, this lecture notes in Civil Engineering, Springle, and editor in the International Conference on Materials, Mechanics, and Structures 2020 from 2020, that is July 14 to 15, in the IOP conference series of Material Science and Engineering. So we warm welcome you, sir, to the third session of third day FDP, sponsored by AECT Atal. Welcome, sir. Please handle the session.
Yeah.
Mic is yours. Platform is yours.
Okay. Thank you very much. So, am I audible?
Yes, sir, you're audible, sir.
Okay,
Stop sharing also. You can share your screen.
Yeah. So, first of all, I thank your organizers for giving me this opportunity, and again, thanks for the kind introduction. And let me just share my screen. So, is the screen visible?
Yes, sir. Yes, yeah. Yeah, it is
Okay.
visible. You can put it in slide mode, sir.
This is actually a PDF only. So, it's
PDF format. Okay, okay. No problem, but still you can. Okay, yeah. That's
Okay,
fine.
so yeah, so maybe for clarity, let me just switch off my video because connectivity, better connectivity. Is it clear now?
Yes, sir. Yeah. It's readable form. No problem, sir.
Okay.
Please continue.
So a very good afternoon to all the participants. So this is the lecture today. Actually, the salient features of recent earthquake codes and the design of special structures. In fact, this is a long topic, so I have to, I'm asked to cover it in 1 hour 30 minutes. After that, the question answer session will be there. So, but the plan is actually it is not an introductory thing because some kind of familiarity with earthquake codes are expected. Okay, so that the special structures as covered in the other parts of the code 1893, that is 1893 part 2, 2, 3 and 4 will be covered first, and after that what I plan is the 1893 part 1 and IS 13920 2016 will be quickly reviewed, or in fact will be browsed through with the salient features. That is the plan today. So I think hope that will be convenient to you, in fact, that plan. So the presentation as such goes with these three. First, that is the design of water tanks as per IS 1893 part 2. Then design of retaining walls, again as per 1893 part 3. And then design of chimney. Okay, so this is what I'm planning to cover in the first maybe 1 hour or so, so that thereafter I can go to the 1893 code latest version and IS 13920 for finer aspects. Okay, so now the underlying principle of the underlying philosophy of the code, I think, is familiar to all of you, where we are going for allowing damage. The basic idea of earthquake resistant design is you are allowing damage, and maybe it is altogether different from the other kind of design where you are not allowing damage. So that is the very basis of it, and all the clauses covered in based on that basic philosophy of earthquake resistant design. And as you all know, the code covers basically the equivalent static method, the response spectral method, and the basics of the time history analysis. So those things are behind. So with those background, we'll be looking into these three aspects of three special structures, basically the water tanks, chimneys, and in fact, the other one is retaining wall. So basically the equivalent static method, as all of you are aware, the basic idea is to find the earthquake force, okay, and then using all the parameters involving the zone factor, response reduction factor, then basically your SA by G you get, and that procedure, equivalent static analysis procedure, is familiar to you. So that is expected, because this particular lecture is not teaching that. In fact, with that background, we are going to the design of the special structure. So when we take the design of water tank as per 2014, it is 1893 part 2. One important aspect is that it utilizes the spring mass model of the tanks. Okay, so where the dynamic loads are modeled in using a spring mass model. Okay, so the hydrodynamic forces are evaluated with the help of this, and then load combination with for load combination with seismic load, the amount of liquid considered in the tank shall be normal liquid level under service condition only. This is one stipulation. Now, the very idea of using that spring mass model is to capture these two forces, which is the impulsive and convective forces. Okay. So when the tank containing the liquid vibrates, actually two types of forces are exerted, that is the impulsive and convective force. And this is in addition to the hydrostatic pressure, Now, this parameter of a, or in fact, this idea of a spring mass model is basically to capture this tank wall liquid interaction also. And the parameters, if you look at, you can see over here, and there are classification as per the code, ground supported as well as elevated tanks are separately discussed. So here, the total liquid mass is divided into impulsive mass and the convective mass. So what is impulsive mass? Which is actually the liquid in the lower region of the tank behaves like a mass that is rigidly connected to the tank wall. Whereas the upper portion is actually undergoing a sloshing motion. So as you can see from the figure, this two behavior is caught in the model. So the lower part, as you can see, it is assumed to be connected by a rigid link, whereas the top portion is by a mass attached with the springs. This is how it is captured. So one is the impulsive mass, the other is the convective mass. And this particular one is for a spring mass model for a ground supported circular as well as for a rectangular work. Okay, now the definition is clear from here, what is meant by impulsive and convective mass. Now the behavior also, here, this is again from the code only, 1893 part 2. The qualitative description of the hydrodynamic pressure distribution on the tank wall and the base. If you see both the impulsive as well as convective forces, the respective pressure distribution will be like this. And the height of the net resultant pressure on the wall, when you consider pressure on wall alone and pressure on wall and base together, these two are separately shown. So in fact, these are the parameters we will be basically using in our design later. Okay, so the basis of that is provided by Hausner, the work of Hausner. Hausner is a very, very famous name in the area of fluid dynamics and earthquake engineering. So the basic idea was from the work of Hausner, where the rigorous theoretical background is kept and then it is codified. Actually, all the parameters now, as you can see later, all these parameters including heights as well as the various masses, because we have notation here as MC, convective mass, MI, that is the impulsive mass, etc. So all that can be laid down very clearly in the form of graphs as proposed by Hausner and then thereafter modified by the ACI committee. Like, though we are following this, whatever our code has adopted is based on or they are basically taken from ACI 350.3, which are slightly different from the original work by Hausner. Basically, the background is by Hausner and slightly modified or improved versions of that as laid down by ACI is utilized in our code. So, what are all these curves? Basically, as if you pay little attention, you can see, depending on the parameter h by d for a tank, tank height and tank diameter for a circular tank, and then tank height by length for a case of a rectangular tank. So based on those ratios, you can see all the required parameters for the design are graphically plotted here actually. So in a design steps, in a design procedure, we will be requiring all these parameters to be found out. And then as usual, we will be proceeding with the seismic weight evaluation and again, basically the base shear and base moment, etc. So that is the idea. So here, what is laid down in the code is actually transferred to you, because the first requirement here is the familiarity with the code. Maybe some of you are familiar with this particular topic, but what is intended here is that the basic theoretical aspect will be covered and one problem each will be solved so that you will get a familiarity. Okay, so in similar line, as we have seen in the ground supported water tank, code also talks about the elevated, circular and rectangular water tanks. There again, similar models are there. You have the convective as well as impulsive water mass identified. This is, in addition, there is a staging also is coming into the picture. So this is the idealization, the two mass idealization for an elevated water tank. Okay, so the charts are the same. Actually. The charts which are being used are the same for the two types of tanks, whether it is ground supported or in fact elevated water tank. Okay, so now other aspects. So again, the underlying principle is that your aim is basically to find out the various parameters, so that parameters to find out your lateral force for which you are going to design, which will be your the basic idea of your what you say, the equivalent static method. So all these charts and procedures are finally aimed at arriving at that step. So then we have to have the time period evaluation. So that is for the two modes. You have the impulsive mode as well as convective modes. So code has given separate formulae for finding out the various time periods. So these time periods are later on used to find out your parameters required for the lateral force calculation. So then here PI, impulsive force, given by this formula, where CI is the coefficient of time period for impulsive mode. This can be found out from the figure. This is actually figure 5 from the code itself. So the CI value can be obtained from here for time period, and all other parameters are straightforward, as you can see. And again, depending on the base fixity condition, okay, that is also, this is an important note. In some circular tanks, wall may have flexible connection to the base slab. So different types of walls to base connections are described in the code. For tanks with flexible connection with base slab, time period evaluation may properly account for the flexibility of the wall to base connection. So this is an additional note provided by the code. But here, this formula is for what? For a ground supported circular tank where the wall is rigidly connected with the base slab. Okay, so now in a similar way, the impulsive time period calculation for impulsive mode for the ground supported rectangular tank. Okay, where the formula is given by Ti equal to 2 pi root of d by g, where the various parameters are over here. Now again, when it comes to an elevated tank, okay, please remember in an elevated tank, you have the staging also coming in the picture, and the stiffness of the lateral stiffness of the staging is an additional parameter. Now, all of you, if you are going to design an elevated water tank, say in seismic zone 3, this is the procedure by which you have to proceed. Okay, so definitely you have to go for the earthquake resistant design as per the code. Then only it is legally correct. Okay, so in that context, you know, so many tanks are there and now codes are there, so you have to be in line with the latest provisions and very important provisions of the code. Because again, repeatedly it's being told, code is a legal document. Okay, so as far as we are as per code, as structural engineers and designers, no, we can be safe. So that is very important point. You cannot deny the clauses of the code. Now, when it comes to elevated tank, certain things. So MI is there. It's impulsive mode. Then there is an MS coming. MS is mass of empty container and 1/3 mass of the staging. Okay. Why all this is coming? Because it is from the very basis of the theoretical background. And in the code, you will see only the end result. Okay, so here my purpose is just to get you familiarized with the code, those important clauses which you should not miss, etc. Now, here the one step you will be requiring to find out the lateral stiffness of the staging. So that I think we can see when we just take up that particular problem later. Now, so in a similar way, the time period calculation for convective mode also is to be worked out. So again, for circular tank and again for a circular tank and also for rectangular tank, the values of the formulae are given. And another important thing is the damping aspect. Okay, this is also when it is amounting to find the final lateral force. All these are crucial. Damping in the convective mode for all types of liquid and for all types of tanks shall be taken as 0.5% of critical. Whereas damping in the impulsive mode shall be taken as 2% of the critical for steel tanks and 5% of the critical for concrete or masonry tanks. All these points will find its role when you actually design. Okay. Now with all these, finally, what we are about to is we have to find the horizontal seismic coefficient AH as per this step, which all of you are familiar with, I hope, Z by 2 into I by R into SA by G, where each of the parameters are stipulated in the code itself. So what Z value to be used, what R value to be used, all are specified. So as far as Z value is concerned, zone factor as per IS 1893 part 1. I is important factor given in as per table 1. Okay, that is again from the code. Then here, as far as R value is concerned, it is response reduction factor is here it is given in the code itself in 1893 part 2 itself. It's given, so you have to refer to that. All kinds of tanks are referred, so R value to be taken from that. And your spectrum can be the same thing which is used in IS 1893 part 1. Okay, so these are again suggested values of R for ground supported tanks. This is again referred in the same code. And okay, I think I can skip that because that is the usual step we do whenever we make use of equivalent static method. Only thing is that how to get your time period, how to, that is more important as far as this tank is concerned. Using that, you will get your SA by G value. Now, another important point here, design horizontal seismic coefficient AH shall be calculated separately for impulsive and convective modes. That is what we have done. Separately, we have got the time periods. Then value of multiplying factor shall be taken as 1 for 5%, 1.4 for 2%, and 1.75 for 0.5% damping. Because your code specifies it for 5% damping, your spectrum. So whenever you want to have different damping values, accordingly you have to use multiplying factors. Because earlier there was a stipulation on damping. If you look back here, particular value of damping. Okay, then to suit with that, you would use a multiplication factor. Okay, so then with that, you will be in a position. So ultimately, you are getting your AHI, that is impulsive, as well as AHC. Then you are going with your base shear. Okay, now when it comes to the ground supported tank, separately, these are the formulae given by the code for what you say the AH value in impulsive as well as convective. Okay, so maybe in between, we just check whether everything is fine. Is everything fine? Am I audible? Is everything fine? Somebody can give a response.
Yes.
It's fine now?
Yes, sir. Yes.
Okay. Okay. So, see, once you get your base shear value in the impulsive as well as convective mode, code gives how to combine it, getting the, in fact, the base shear, finally design base shear. So, which is by the SRSS rule, okay, sum of the square root of sum of squares. Similarly, in the case of elevated tank also, the formulae are given by the code for both base shear in the impulsive and convective mode, and then you will be combining it like this. In a similar way, when it comes to base moment also, the separate formulas are available as per code, and then again you combine it using the formula given by the code. Okay, so further into it, there are finer aspects are there, but maybe a first level introduction to water tank design. This much is what I intend to cover. Then in similar lines, let us quickly see a problem. Only it is meaningful. Okay, so here again, finer aspects will be anyway shared to you. Finer aspects are finer aspects will not be able to touch in all detail, but the procedure can be quickly told. So here what you have is an elevated water tank with 50 meter cube capacity, and all other stipulations are given. Staging is utilizing ordinary moment resisting frames, OMRF. Okay, then seismic zone is zone 2. Steel and concrete grades are M20 and Fe415. Concrete density is given. Then again, all the parameters, geometrical parameters of the staging and also the tank. Tank details are further given. All the structural dimensions of the the structural members are given, because you have to estimate the force, and the geometrical aspect is all here available. So the tank is having circular in shape and having a depth of water depth of 3 meters, and the staging has a height of 12 meters, and the foundation the footings are below the ground by 2 meters. This is the overall picture, and you have to analyze the tank for the seismic loads. Okay, so here comes the preliminary data of all the various elements: roof slab, wall, floor slab, gallery, floor beams, braces, and columns. So these columns are circular, okay, and braces are in plan view. It will be it will be like this, in fact. So you have the 4 columns, and you have braces like this, and the braces are actually having rectangular cross section. This much is regarding the tank. Now, first step is to calculate the weights. So that is a meticulously we have to work out all the weights of all the elements, okay, including water. The total weight has to be found out. So each element wise, the values are here. Okay, that is the first step. Now, further calculations. So we are actually designing, or in fact estimating the earthquake forces for an elevated water tank. So staging weight separately should be obtained. Staging. So that is weight of columns plus weight of bracing. That is basically these two. Sum of these two is your weight of staging. Then weight of empty container is a remaining thing. That is 502.1 kg. Now, weight of container plus 1/3 weight of staging is required, because this is the one parameter as per the code required. That is 1/3 weight of staging plus weight of container. Now, next is center of gravity of the empty container. So that is again first moment we have to take about this level, because about this level you have the wall boundary, then slab, rooftop, everything is there. So get the get the CG of the empty container with respect to the base, which is worked out to be 1.18. This is the same, actually it is rounded off 1.19. Then height of the CG of the empty container from the top of the footing, because you know it is as per this diagram, this height is 2 plus 12, 14 meters. So 14 plus this height of CG. So that is how the height of the CG of the empty container from the top of the footing will be 15.18 meters. Okay, now this why this is required is later on now we have to get the stiffness of staging as one step. So that is required. Now, other calculations for this spring mass model. Now, as per code, when you proceed now, code we have shown, we have seen the charts earlier. Okay, all the charts where the various impulsive and convective mass as well as distances. All these suffixes you can note, which is HC, HC, HI, etc. So it all depends on what is your the H by D ratio. So for the height 3 meter and the diameter of this circular tank is 4.65 meters. So 0.65 meters, you have to get the parameters from the various charts. So Mi by M. So M is actually your total mass, okay, which is actually, sorry, Mi is your weight of water, which is 50948 kg. So as a function of that, you can always get all the required parameters Mi, MC, HI, HI star, etc. from the charts, the various charts available with the circular tanks. If it is a rectangular tank, the respective chart has to be referred. Now, this value already we got, mass of empty container with 1/3 mass of staging. Now, this is expressed in kilograms. Okay. Now, the next parameter required is the stiffness part, because now we have reached a stage where all the individual parameters are obtained, like mass, height, etc. Then now the thing is we have to find the time period. So time period, make use of this formula for the elevated water tank, where this particular parameter ms is the one which we have obtained now, that is mass of empty container plus 1/3 mass of the staging. So all other parameters are now ready other than Ks. Now how to get this Ks is basically by performing an analysis. Okay, so that is what one manual sort of calculation is just kept here. Okay, that is if you that means you have to apply some force, okay, and get a deflection, because you know the entire model, you know the column dimensions, you know the bracings, etc. So either model it in a software like STAD or SAP somewhere, and then you apply a force and obtain the deflection. Okay, so from that, with an equivalent single degree of freedom model, you can get the stiffness. So that means here, as per that analysis, a 10 kilonewton force produced a deflection of 0.0033 meters. So what happened is the definition of stiffness comes as 3030 kilonewton per meter. And this was done for a 2D model as per this model like this. Actually, you have 4 columns, but for 2 columns only this value is being arrived at. So that for a pair of 2 more columns, it will be twice. So that is the way the 60 kilonewton per meter that is worked out. Now this can be obtained maybe by a hand computation also, by using a standard structural analysis method, but it may be cumbersome or lengthy. So it is always preferred to use any software to find out the scale. Please see that this is a step which is to be very meticulously done, because this will be getting your time period, and that time period only will be giving you your SA by G, etc. And then ultimately it is that horizontal seismic coefficient, which is a function of all these. So each and every step is very important, meticulously to be done. So then time period calculation, and again, there are two time periods, that is the impulsive as well as convective, both has to be separately found out. And then you have to use the AHI, get the AHI value, right? So in the problem, all these were given. I was given to be importance factor was given to be 1.5, zone factor 1, and R we are taking as 2.5, since in the problem it was told that it was only ordinary momentous steam frames. Okay, then damping for 5% stiff soil, so it is it's again maybe given or assumed, so then value is 2.09. So that finally your AHI you will be getting as 0.06. This is for impulsive mode. Similarly, for convective mode, when you use, you are getting 0.04. But please see, for convective mode, you are not supposed to use 5% damping. It has to be 0.5%. So accordingly, there should be a multiplication factor of 1.75 to be used, which I already mentioned earlier. Okay, so when it comes to convective mode, AH convective is going to be 0.0. Now, if you see, then ultimately it is applying the formula, base shear in impulsive mode, base shear in convective mode, and then combining you get base shear as 60 kilonewtons. So maybe roughly 6 tons is your earthquake force, base shear, which is appearing for this particular tank. So it is to be designed for that. Now, one simple observation, if you see it is coming to be around 5% of the seismic weight, the total seismic weight. Seismic weight is actually obtained by these two. In fact, this 499 plus, in fact, yeah, this 622, 25.86, that is your seismic weight. So you can see that total is 1126 roughly. And this 60 kilonewton is obtained as around 5% of the total seismic weight. Why this is stressed? Because you know that to the tune, it will be like that. It will be maximum 5 to 5, 6, 7% of the seismic weight. If at all you make any mistakes in between, you can have a kind of quick check and see whether it is the order fine, whether the order is fine or not. Okay, so I think with that water tank part, that is design of an elevated water tank, following the various stipulations of the 1893 Part 2 code is covered. Okay, so I repeat, it's not a complete thing, it's only a peripheral sort of thing, because it's a vast topic, many details are there. So my intention here is to impart a familiarity. Those who are very new to it, maybe in a second listening, it will be clear and you will gain the confidence of designing an product. Okay, now quickly on to the next topic, which is the design of retaining wall, as per IS 1893 Part 3. Okay, maybe some quick basics. Not going to read all these things. Now, retaining wall, all of us are familiar with, and especially in the earthquake scenario, why it is important is because of the soil survey of damage during past earthquakes have shown that retaining walls have moved out away from the backfill. This is what is being observed. So based on these observations, the philosophy of earthquake resistant design adopted considers the active earth pressure during earthquake to increase and the lateral resistance to decrease. This is one key point. Okay, so during earthquake, the active earth pressure is observed to increase. That means that on the reverse, the earth resistance is observed to be decreased. Now, how to account for this in the seismic resistant design? Here comes the answer. It is one approach is to consider a reduction in the angle of internal friction. Is there any issue? Am I audible?
Yes, sir, you're audible.
Okay. Okay. So, see, the key point here is, since the active pressure is observed to increase and the soil resistance to decrease, a smart way of accounting for that will be to consider a reduction in the angle of internal friction of the backfill material, because you know backfill material will have an angle of internal friction. So the enhanced earthquake force can be dealt by assuming that, okay, the angle of friction gets reduced. Okay, so that's why we introduce a phi dynamic. Okay, phi suffix dynamic, as it is little reduced from phi, so which is actually phi minus tan inverse alpha h, where this alpha h happens to be your horizontal seismic coefficient. That is the essence of it. And the entire the design for retaining walls is for earthquake forces, rely upon that. Okay. And if you look at the code, these are basically the code page only, just for familiarity. Section 22 of IS 1893 part 3. Please see, it is only applicable for phi soils, that is cohesionless soil. This particular section is only for cohesionless soil, and for cohesive soils, section 25 is to be referred. So we are not taking it for the time being. So we are only looking at the cohesionless soil, that is phi soil. Here, the whole idea is we have this parameter P A gamma dynamic. So the active earth pressure is observed to be increased. So as per code, this expression will be giving the total dynamic active earth pressure. See, P A gamma dynamic is dynamic total active earth pressure in kilonewton per meter length of the wall. Fine. This is the cross section. So in the perpendicular direction, the retaining wall is running, and this diagram itself is from the code directly. This equation will be giving you the total dynamic active pressure, wherein the CA is the coefficient of earth pressure, which is covering all these parameters. Okay, you can see all of them are there. In addition to that, you have your vertical coefficient or vertical seismic coefficient, which is taken as a function of the horizontal coefficient. Usually it is taken as 2/3 of AH. Okay. If you know the idea of horizontal seismic coefficient, all of us have AH. And AB also comes into picture. So AB is taken as 2/3 of AH. And other parameters are angle of internal friction, then alpha, it is angle with the face of the wall, which makes with the vertical, it's this one. Then I, slope of the landfill. Then delta, angle of internal friction between the wall and earthfill. And of course, lambda is defined as tan inverse AH by 1 plus or minus AB. Because of this plus or minus AB happening here and here, there will be two values of CA. Okay, so the code suggests that both the values of CA to be found out and the maximum to be taken. Okay, so one with plus AB, the other with minus AB has to be taken, and CA has to be separately found out and then to be used in this particular equation. Okay, and again, the next part is, I already told you, it is the total active dynamic earth pressure, so that it will be having a static component as well as an dynamic increment. That is the next point to be noted. And this slide I am skipping because instead of looking at analytical expression, there is a graphical way of getting the CA value, which is again mentioned in Annex C of the code. It's just kept for information. Okay. Now, the point of application only I was just telling you. In the expression which you have already seen, you can see that AH, AB, and gamma are the three parameters which is corresponding to the dynamic state. Okay, because otherwise it is static. Because otherwise we deal with static earth pressure. Here, these are the three parameters taking care of the dynamics of it. So in the sense that in the expression for CA, if you set these parameters to 0, then it will be representing the static part, okay, and the remainder will be dynamic increment. That's the idea. Okay, so then the remainder is the dynamic increment. The static component of the total pressure shall be applied at an elevation of h/3 above the base of the wall. And the point of application of the dynamic increment shall be assumed to be at an elevation of 0.5 h above the base. So how you get the static component is by setting the 3 dynamic parameters at 0. And then from the total, you subtract this dynamic part, you will get the dynamic increment. Okay, that's it. Sorry, from the total, if you subtract the static part, you will be getting the dynamic increment. And then finally, you have to mark these lateral forces at the respective heights, and then it can be the base shear as well as the overturning moment can be obtained. Okay, so that will be quickly, in fact, exemplified or in fact worked out in the problem through this example. So we have to estimate the dynamic, static and dynamic active earth pressure and locate their point of application as per the provisions of IS 1893 Part 3, 2014. All the parameters are height, slope of earth, inclination, angle of internal friction, unit weight of soil, etc. So as I told you, first thing is getting the total dynamic active earth pressure, which is total. So total represents, it will have the dynamic parameters AV, lambda, and H. Of course, AV is implicitly present. H is implicitly present in this. So we have a plus or minus symbol coming. So therefore, what we do is separately we find out the positive values. For positive and negative value, we will get. So in one case, it is 1 plus AV. This is actually AV, not AH. Okay. Secondly, it is A 1 minus AV. So then first case you are getting CA value as 0.562. Second case you are getting CA value as 0.517. So as per code, the larger value to be taken. When you take the larger value, then you work out the PA active, that is active dynamic of pressure total value is 647.42 kilonewton per meter. Okay, this is what you do. Now the thing is, how is it getting acted upon? Which has got 2 components. Excuse me, am I audible?
Yes, sir.
Okay. Now, total force is obtained here. Now, as I told you, the same expression, you have to put the dynamic parameters AH, AV, and lambda as 0. So, with that, you get a new CA, and then you get a PA static. That CA value you use in the same expression, and you get the static active earth pressure, which is 535.68. Now the difference is total minus the static, which is 111.74 is the dynamic increment. Now, as per code, the dynamic increment will be at a height of 0.5 h from the base, okay, and the static component will be at a height of h/3 from the base. Okay. Now, this is the code stipulated procedure for finding out the forces, active or pressure forces. Again, please remember, when you are in an earthquake zone and when you are supposed to design, when you have to design the retaining wall as per the earthquake standards only. So that is why you require, and again, water tank, retaining walls, stack-like structures, chimney, etc., all critical structures, okay, especially for lateral loading. So there is no way you can avoid these stipulations whenever you do, okay. That's what I told. Legally, you will be safe. You should be doing these designs as per the earthquake resistant codes. As far as we are in earthquake zones, we're bound to do that. Now, last one in that section is the design of chimney. So if I am as per plan, I'll be able to finish these in 1 hour and then take up the code quickly for another half an hour. Okay. Design of chimney as per 1893 part 4 2015. There again, these are from the sections from the code itself, and the code talks about what is meant by a stack-like structure. The stack-like structure is one in which the mass and stiffness is more or less uniformly distributed around the height. So here also, now I can go quickly. The whole idea will be to evaluate your AH part, okay, and then proceed with that base shear and moment calculations. Okay, so we will quickly see that. So code tells the time period of vibration of a stack-like structure as per this formula, okay, where the fundamental time period is given by a CT into under root W2H by ESAG, where CT is a coefficient depending upon the slenderness ratio of the structure. Because stack-like structure is a slender structure. So based on that slenderness value, coefficient CT is to be found out. And WT is a total weight. Then H is the height of the structure above the base. ES, modulus of elasticity. And A is the area of cross section of the base of the structural shell. Usually chimneys and stack-like structures will be having a double, in fact, double wall. There will be usually a lining also inside. Okay. So this formula is only applicable for stack-like structures in which the mass and stiffness are more or less uniformly distributed. Okay. Now these are the different tables as per the given in the code. Because I told you there will be a CT and CV. This is actually CT. Okay. So this is a printing mistake. So this is the table 7, which gives the CT value and CV value. CV value will be required later on. Here we have already encountered CT. CV will be coming later on. Then again, specific to stack-like structures, the importance factor, then R value are given by tables that 9 and 10 respectively. Okay. Then the horizontal seismic force evaluation, as always, SA by G into Z by 2 and I by R. Okay. Now, after that, how to get the design force, design shear force and moment. That again, a simplified method based on the equivalent static method is given in the code. It is given in a tabular form, as well as the direct formulas are given for you to do that. So these are the, after evaluating, see your AH comes here, because the initial steps will enable you to get your horizontal seismic coefficient. Then for each of the parameters, or each of the base shear and moment, these formulas can be used. And these are in line with the background theory, basically, okay, of from which only all these are coming. Okay, so if you look at this, I can tell in the problem to continue, but I'll come back to this table when we take up the problem. So here this B has a CV already we have seen the first table. CT and CV are there. AH is calculated, and WT and DB, where WT is the total weight of the structure, including weight of lining and condense above. DB and DM are basically the distribution factors associated with the shear and moment, V for shear, M for moment. And they are given directly in the tables here, table 11, both DM and PV values, because for each level H you can find out. Okay, this is for each level H. Actually, you can see the simplified method can be used for stack-like structure. Design shear force P and design bending moment M for such structure at a distance X from the top shall be calculated by the following formula. That means that for each of the X value, it is a stack-like structure. So it's a tall structure. So at each level where X is measured from the top, you can find out the value of B and M, and accordingly you can design. So you need not design for the entire force at the base. It need not be like that. And usually it will be tapering also, as you can see as you move on towards top. So code directly gives that provision that depending on the distance from the top, you can get the respective value of B and M. Shear force, the force, as well as the design shear force and moment. Okay, so these are the tables and the formulae involved. The same table is obtained actually based on this particular formula. This is what I told, that factor X by H. So for top it will be X0 and bottom it will be H by H. That is 1. So this result only is tabulated in the table 11. Right. Now again a quick example. Reinforced concrete chimney of height 28 meters and in seismic zone 5. The outer and inner diameters are specified 3 meters and 0.8 meters. Then it has a lining, brick lining 0.1 meter thick. Shell thickness is 0.3 meters. Evaluate the earthquake force on this chimney as per provisions of IS 1883 Part 4 2015. Modulus of elasticity values for both the concrete material as well as lining is given. So it is quick only, you can quickly see the so it is as per the codal procedure. First thing is period of vibration, CT into under root WH by ES H. So area of cross section to be found out, as you know, it is a double wall. Internal and external diameters are there. Then we can get the I value, okay, moment of inertia value 2.347 meters per 4. Then radius of gyration. Radius of gyration as root of I by A, where you use the area at the base. Then slenderness ratio, L by R, height is 28 meter, radius of gyration is 0.96, so you get 29.167. And then you get the coefficient CT. So it is slenderness ratio is 29.167. So I'll just take you up to that table again, where you have seen your CT. See, our slenderness ratio K is around 30, okay, 29 point something. So it is close to this 56. CT value is 56. So we go with that CT, 54.3534, and weight of chimney, because you have to get your WI, so that weight of chimney, weight of lining all together, you get your total weight of chimney as 162.84 tons. And you use the same formula, CT into under root, this thing, so to get your time period. Okay, now for this time period, you have to get the, again, hard rock is assumed. And for this time period, you get your SA by G as 1.96 and then 0.36 by 2 I by R into SA by G, you get 0.5 as your AH value. Now that AH remaining the same for different height from top, you can get the V value of P and M. Right? So one sample calculation I have just shown you here for the one sample calculation. For say for example, X by H is 0.2. Our height is around 28 meters, so 1/5 of the height from the top. So if that X by H is 0.2, then For x by h, you can get CV. From the same table above, for x by h is equal to 0.2. That is this table. Actually, for our slenderness ratio, again, is the same, around 30. Our CV value is close to this one, 1.34. So our CV value we got now from the same table. CV is obtained as, say, 1.342. That is for this slenderness ratio of 29.16 from table 7. Then you say one sample calculation for V, that is CV into 0.35 into, that is AH, into W into DV. Okay, so now for DV, what is DV? DV should be obtained for x by h of point. That is from the above table. Either you use this one, okay, DV to be obtained using an x by h for the whichever case you are taking, whether it is raft or fixed base or pile. Accordingly, take this or take it from this table. Again, it is given for x by h value of, say, 0.2. For DV value for fixed, like that you will get. Okay, so that way is the last step. So that way you are getting it as 49.2 tons. Right. Here I have directly used it from the formula, whatever formula. In a similar way, the moment at corresponding to x by h of 0.2 is obtained like this, which is actually again here to get. Now the thing is, where h bar here this requires an h bar calculation also. What is h bar is height to the center of gravity of the structure above the base. That has to be separately found out, because you know chimney will be of this shape, say, and by using the first two moments you have to get the CG height, and that is your h bar. Okay, because you know all the parameters, thickness, lining, everything, and taking first moment of the whole thing about the base, you can evaluate your h bar. So that h bar is here. So once you get the h bar, you can get your m corresponding to x by h point. Okay, so that's it regarding those topics. In fact, I plan to cover it in 1 hour. Almost it is done. So hope this particular 1 hour lecture so far could in fact get you some idea of finding out or to do the procedure, okay, for the design of an elevated water tank, a chimney, as well as for a retaining wall, as per the provisions of earthquake codes, Indian earthquake codes. And I repeat, wherever you are doing a design, okay, when you are in an earthquake zone, as per the Indian standard, you are bound to do that, whether it is water tank, retaining wall, or chimney. Okay. So I think I'll just I'm sure maybe I have one more. I will now take up the code, the 1893 part 1 and 13920 2016, just for some important features. Okay, so let me just take the other one. Okay, is it visible now? 1893 part 1?
Yes, sir. Yes.
Okay,
It's visible.
okay. See, again, I don't know how many of you are well versed with this particular version of the code. Maybe some of you would have got familiarity. I'm not intending to go for a comparison between the previous code. In fact, such documents are there with our own, some of the students we have done a comparison study between 2016 and 2002. But anyway, that is not intended here. Here, with the latest version, many things are getting explored, and again, there are points of discussion at many classes going on. So what I do plan is to just browse through it, okay. And some point I have already highlighted, which is of some importance, okay. And again, some familiarity with the code is expected at this level in this particular lecture. Okay, somebody who is looking at the code for the first time may not be, in fact, it may be difficult, but still you can be listening, and then you can catch up later on. So if you see the various sections, again, all the latest codes are referred, if you can see. And I'll tell you as an advanced information, for any code, if you refer now, maybe the first step would be to see the amendments, okay? Because I'll just take you to the last page of this, okay? Hope you are all seeing the last page. I think 1893 part 1, 2016. These are amendments, only one page is there. But the thing is, whenever you have read a code, or when you have a printout, first thing is that make the corrections in a prominent color in the main document, okay, before you start reading it. So whatever is there, you have to go and correct in because all these amendments at the respective pages, go and edit before you start the reading. Okay, so with that, let me go back to the first page again. So section 3, all the terminologies are in fact explained, definitions, and you see that some of the familiar terms like MC, etc., are not now referred, okay, in this particular version. So just browse through, and wherever some important aspects coming, and stop on. Okay, so all of you should, in fact, read through the general principles and design criteria, because it is reiterated what is the general principle once the codal provisions are laid down, so that should be seen. Then there are important clauses like addition to existing structures, you see. Okay, so I'm not going to read all those things. Whenever you make additions to existing structures, and in the lateral load point of view or earthquake point of view also, you be careful. So all those stipulations are there, and these are very relevant, especially when you think of designing or in fact adding a floor to an existing structure. For example, you have a 5-story hospital building, okay, and then usually we go with, okay, one more story is required, so we check with the foundation design, find maybe some soil investigation further, and you go with that. But no, in the context of earthquake resistant design, especially for lateral loads due to earthquake, these provisions also have to be checked. Okay, so this is one kind of caution, or maybe you have to keep in mind. So there is a specific section for that. Here and all, only legality comes into picture. I'm repeating, because all of us are bound to, in fact, maybe sometimes without knowing, we will be violating the existing provisions. Okay, so if we cannot say that we were not knowing about such a provision, then it is required. We cannot say that. So you have to be, or all of us have to be careful enough to see that the code, which is also a legal document, which is in fact, which is sticked on to, in fact, Okay. Then further things. Yeah, no, maybe some of the important things I have highlighted. So what this code is mainly covering is the equivalent static and dynamic analysis method, whereas the dynamic analysis can be performed in 3 ways, namely response spectrum method, model time history, and time history method. But in this standard, the equivalent static method, response spectrum method, and time history methods are adopted. Okay. Now, one important clause, equivalent static method may be used for analysis of regular structures with approximate natural period TA less than 0.4 seconds. So the applicability of equivalent static method is here. Okay. So these are some clauses which are having implications. These are not in its own ending statement, but what I'm telling is these are some of the important points we will explore when you further read it. Okay, and again, moment of inertia calculation also. There is some stipulation in RC and masonry structures. 70% of I gross of columns and 35% of I gross of beams. This is for modeling. Okay, and again in steel structures, I gross of both beams and columns. Because moment of inertia portion when you are taking, it shall be taken like this. Do not take the full 100%. Okay. Then you can see this is our spectrum. There are 2 diagrams. One is for the response spectrum method, and the other is for the equivalent static method. So you have spectra for equivalent static method, and this one for 2B, figure 2B, spectra for response spectrum method. And if you see 2002 version, there was a single diagram. Okay. Now, the whole idea was of our equivalent static method. Now you see our aim is to get your design base shear, okay, or BB value, design lateral force. And if you see all the 3 special structures, what we have seen, essentially we were doing this. We were working out our horizontal seismic coefficient and multiplying with the seismic weight. Then, and the code, these causes and all, these time period calculation part, and again, all these figure 4, these are all fresh, in fact, new compared to the previous version. And then again on equivalent static method, okay, you should do this. So now as per this method, first the design base shear VB shall be computed for buildings as a whole. Then this VB shall be distributed to the various floor levels at the corresponding center of mass. And finally, this design seismic force at each floor level shall be distributed to individual lateral resting elements through structural analysis considering the floor diaphragm action. Now, here also, see, this method shall be applicable for regular buildings with height less than 15 meters in seismic zone 2. So a very crucial point, okay, to be remembered, because that means that if your building is in seismic zone other than 2, then definitely you have to go for dynamic analysis. That is the implication. Okay, but it doesn't mean that you should not do an equivalent static analysis. You have to definitely perform an equivalent static analysis. In addition to that, because that will be required for finding out a factor for multiplying the individual forces as a result of the dynamic analysis. I'll make it clear. The point of discussion here is, if you have a building either greater than 15-meter height, that means roughly 5-story height, more than that, okay, and even less than that, 4-story height and more, or if it is in zone other than 2, definitely you have to go for dynamic analysis. Okay. But at the same time, you have to perform an equivalent static analysis also, V bar by VB, okay, in order to get the actual forces. So these are some of the implications. That's what I told those who are familiar with the methods only will be straight away following it. Others can just keep these things in mind, and then whenever you happen to go through the code or codal provisions, keep the things in mind. Okay. Then after the equivalent static method, code talks about the dynamic analysis method. So altogether, it is about these two, the static and dynamic analysis methods with all its finer aspects. Then it runs into the various annexures. All these annexures were there. Few of them are new at the end. So here you can have the annexure B. Here showing the principal tectonic features in India. This one is for mythological groups. This one again for MSK intensity scales. And towards the end, finally, the list of towns with the population more than 31 lakhs as per census 2011 and their seismic zone factors. This was there in the previous version also, but this is the updated version. And again, annexure F is new one, that is simplified procedure for evaluation of liquefaction potential. Okay, so maybe in 15 minutes, okay, this much is a quick scan of the, in fact, the code, because of time constraint, nothing more than that can be shared. But the thing is, at here and there, some important crucial points are there, which whenever you learn in detail, please apply your mind. Okay. Next one, I think the last one I will take up the ductile detailing code. I hope this is also visible. The right document is seen. IS 13920/2016. Ductile design and detailing of reinforced concrete structures subjected to seismic force code of practice. Here also some implications. Let me browse through and then some of the implications let me tell you. So whenever you are demanding, or in fact your R value, whenever ductile detailing is required, you have to do as per this stipulation. So the very idea of the seismic resistant design is that at the same time you bring in ductility aspects also. So if you can afford to do the ductile detailing, then you can have the R value reduced so that you can have the earthquake forces can be estimated with a reduced value. That's the idea. So if you are using ductile detailing, you can use as per the code R value 5 in all your analysis. Now here some stipulations in the general specification, some stipulations regarding the use of material. So here as per the code, here only it is told, you see it is not an IS 1893 it is told, rather it is told here that which is the grade of steel and grade of concrete that can be used. So minimum grade of structural concrete that can be used is M20, but M25 for buildings. And again, here also some stipulations are there. Then when it comes to steel, as per this code, you can see use all the three grades. Okay, 415 you can use, 500 you can use, and FE 550 also can be used. But there are stipulations on elongation percentage, as you can see here. FE 500 and FE 550, that is high strength deformed steel bars produced by thermomechanical treated process having elongation more than 40.5%, that is the stipulation. Now, here and there, some very subtle points are there. Such a point is over here. It's very important. In RC framed buildings, lintel beams shall preferably not be integrated into the columns to avoid short column effect. So most of you would have come across the word, the terminology short column effect. So when you have a series of columns and one of them is short compared to the other, it will be stiff and it will be attracting more earthquake forces. So the demand on it will be high. So there are some very subtle issues in the which is there in connection with the short column effect. And most of the post-earthquake scenarios revealed that failures in columns have happened because of the short column effect. And now a common situation in which it can happen is with the construction of a lintel. That is the context. So very interesting context here. That is, in RC frame buildings, lintel beams shall preferably not be integrated into the columns to avoid short column effect. Okay, so I can just demonstrate by here itself. Say you have a series of columns in a building, maybe fixed, and your beam level is coming, say at this level, which is actually 3 meters from the bottom. And imagine you have a lintel here. Lintel. Now, if you are constructing the lintel, say at 2.1 meter from the base, and you are constructing it integral to the column over here, what happens is, compared to this column, okay, column 1, column 2 is a short column, correct? So the thing is, when you, in the actual practice, in reality, this column 2 will attract more force because it is stiff. But the issue, I'll tell you, the issue is, while modeling, okay, while modeling in a software like STAD or SAP or whatever, you may not model this. Okay, agree, you may not model this. You may not provide a lintel there. So in modeling wise, all columns are similar. There are no short columns, right? And your demand will be accordingly in the model, the demand will be accordingly. But when in the construction, when you are constructing, you construct a lintel, say, and such a situation comes. So what happens? 2 becomes a short column. So there is a variation from the modeling and hence your design. Your design will be as per the actual, as per the force get received by this column, lateral force, whatever. Whereas in the actual practice, it will be more. So the point mentioned here is, code itself is telling whenever lintels are there, preferably they should not be integrated into the columns. You are just keeping it on stopping here, fine, because purpose of a lintel is to keep it, no, you have to have it over an opening. So do not bring it and connect to the columns, rather leave it at this point, it's fine. That is the first part. If at all you are integrating it to the column, then it shall be included in the modeling and analysis, then it's fine. So that the model will capture it as a short column and then accordingly the demand will be there. Okay, or accordingly the design will be there. So there are such points. Okay, so I thought that you share, I will share it with you. And again, another important thing is there are stipulations on the beams, depth to width to depth ratio, minimum width of beams, etc., which are there in your IS 13920, this code. Now, the important point is such stipulations are to be checked before you preliminary proportion your beams and columns. Okay, so your preliminary proportion, all of you know, before modeling in a software, you should know, you should fix up the dimensions of beams and columns, which we do basically using the gravity load analysis. But such criterion also should be brought in there. Otherwise, later on, this will become violations, right? And especially in columns also, it is like that. So when it comes to beams, it is like this. Okay, so my point is you have to bring this in the preliminary proportion, because you know you say, for example, column load you calculate based on this formula 0.4 CK AC plus 0.67 FY ASC. This is the one which you basically use for fixing your column dimensions, correct? Where AC is the area of concrete, ASC is the longitudinal steel. So therefore, in addition to this one, you have to see that the column dimension stipulated by this code, which is IS 13920, is also satisfied. Okay, for which I will quickly take you to there, because that clause is also very important. Yeah, here you see the minimum dimension of column shall not be less than 2 points are there, 20 times dB, where dB is the diameter, the largest diameter longitudinal reinforcement bar in the beam passing through or anchoring into the column at the joint. So if you have a beam column and the beam is going through it, and the largest diameter of the bar in the beam is dB, say it is 16 mm, imagine, then into 20 times, that is 320 mm should be the minimum dimension of the column. Okay, if it is so, and if it is, and the bare minimum should be 300 mm. This is one very important stipulation as per many practical consideration. Code is insisting that minimum dimension of the column should be 300 mm. So these stipulations also should come into picture when you design the or in fact proportion your column for preliminary dimensions. In addition to that, one more is there. See, the ratio of smaller dimension to larger dimension of the cross section of the column shall not be less than point. It's actually not 0.45, it is actually 0.4. That's an amendment. Okay, so this is another clause. This is another clause. All these should go in line with your preliminary proportion. Okay. Otherwise, later on, when you see that your structure is to be designed for earthquake forces, then there will be violation. So, very important point is that IS 456 and IS 13920 2016 should be simultaneously referred for preliminary proportion. Okay, otherwise you'll be missing. Okay, so then further these sections, in fact, detailing part is actually in much detail given in the appendix, in the amendments rather. Because these came in 2016, and along with that amendments also came, because better pictures are available at the end. You can see the amendments. You see there are a lot of amendments in this particular code. See, better clarity pictures are there available. Around 5 pages of amendments are there. So in the same code, you have the amendments. Okay, amendment one thing, and amendments may be coming further also. So you have to be vigilant on that. So better quality pictures with without errors are available at the amendments. Okay, and you can see a lot of amendments have come in that particular code. Okay. Maybe let me just check if anything else I have marked. Okay, and again, one more important thing I'll tell you. See, as far as this design of columns and beams, design and detailing of columns and beams are concerned, again, you should be referring to this code rather. Okay, with all the details, because mostly we are in zone 3 at least. Okay, so that tail detailing is a must as per the code. So definitely you have to stick on to these stipulations rather. Okay, so even the design steps, design of the column longitudinal elements and beams all are dealt with in all detail here. Okay, so you have to refer to these steps only while going the detailing. Okay, so that is more important. Then again for the beam column joints of non-resting frames. Again, then special shear walls. So maybe because of time constraint, otherwise there are a lot of in fact minor aspects, but maybe within this limited time frame, only kind of an introduction to how to see the code and maybe some of the important aspects. Okay. So I think that's what I planned for today's lecture. So if questions are there, questions are welcome. Hope to some extent this was to use to you. Yeah, please.
Thank you so much, sir. The session was very informative, and you have beautifully covered the design of water tanks, chimneys, retaining walls, and the salient features of the codes IS 1893 and 13920. Now, the forum is open for discussions. Participants can either type their queries in the chat box or unmute yourself and ask questions. Participants? Yes, sir. We have a question from Ms. Ramya Ramachandran. As per IS 3370, minimum grade of concrete is M30, but in the example, why it is M20?
Yeah, that is different only because water retaining structures. The other one, the clause is that building it should be minimum M25 and bare minimum is M20. This will be superseding. This clause will be superseding that. That is true. Okay.
Okay, thank you so much, sir. Participants, any more questions? Yes, sir. One question from Ms. Arya Siddhar. Is there any code for testing of bricks?
Is it a general question or anything specific to this topic? Actually, yeah, as per we have no standard codes are there for bricks. But are you asking this in this context or it's a general one? Okay, general one. Codes are available. Yeah, as per that only you usually check all the parameters, like compressive strength and other durability aspects of the brick. Okay, that is available.
One more question from Ms. Ramya Ramachandran.
Yes. Ductile definitely. Yeah, definitely. Because whenever you want to use the respective R value, the table itself shows that we can the R values are different according to that only. Whether you are following ductile detailing or not, especially when it comes to staging. No, staging, the same problem we have used. It was OMRF. That's why we used 2.5 as R value. But if it is higher value, means you can. In fact, if you are using ductile detailing, you can afford to have slightly larger value. Yes.
Any more questions? I hope there are no more questions.
Okay.
Thank you so much, sir, once again. The slides and recordings will be shared to all the participants later. The feedback link is already shared in the chat box. Please complete it by 4 p.m. And tomorrow is the 4th day of our AICTE sponsored Adult Faculty Development Program on recent advances in earthquake engineering. See you all tomorrow. Please join by 8:55 a.m. Thank you all. Thank you, sir, once again. Thank you so much.